The Rocky Mountains, the backbone of North America. Rugged, spectacular, and majestic. Today, geologists are cracking open these rocks to expose their secrets. How did the remains of sea creatures end up in mountain peaks, thousands of feet in the air? When did the Rockies form? Are they still rising today? And if they are, could the great forces that built the Rockies one day split North America in two? The Rockies, one of the greatest mountain chains on Earth. They stretch over 2,000 miles from the northern tip of British Columbia to the Rio Grande in New Mexico. Up to 300 miles wide, they form the Continental Divide, the Great Barrier between East and West. In Colorado alone, there are 58 mountain peaks over 14,000 feet tall. That's around 2.5 miles high. The Rockies were created by the most powerful geologic forces on Earth. Their dramatic story takes us on a journey from north to south through 200 million years of geological history. From their birthplace in Canada to the youngest peaks in the United States. It's a journey that takes us back into the Earth's ancient past. 200 million years ago, there were no Rockies. Even the continents looked different. There was just one giant landmass, Pangaea. But not for much longer. A vast rift is opening up, tearing this supercontinent apart. Over the next few million years, Pangaea will break apart into many smaller landmasses, eventually forming the present-day continent of North America. Earth's surface is broken up into vast pieces called plates. They sit on top of the Earth's warm, dense mantle. As the planet gradually cools, convection currents in the mantle slowly move these plates across the surface of the Earth. Where plates meet at their edges, there are often immense tectonic forces. These tensions can tear continents apart, but they also build mountains. Kirk Johnson, chief curator of the Denver Museum of Nature and Science, explains.
The action of continents crushing together or continents being hit by oceanic plates, those kinds of forces create basically planetary traffic accidents, and the wrecks result in mountains forming.
Evidence of the power of these immense forces can be found in one of the oldest and most northerly parts of the Rockies, Yoho National Park in British Columbia. Here, the fossils of thousands of peculiar prehistoric creatures lie in a cliff face near the peak of Mount Stephen, 8,000 feet above sea level. Geologist and mountain guide Paul McNeil specializes in the fossils of the Burgess Shale.
We see fossils here that we find almost nowhere else in the fossil record, and unlike any animal that's alive today.
This spiny creature is called Hallucigenia, and this bizarre specimen, Wiwaxia. These fossils offer clues to how the early northern Rockies formed, because they're not the remains of mountain-dwelling animals, but of sea creatures. They lived and died in a shallow tropical sea over 500 million years ago. The rocks that contain these extraordinary fossils formed on the sea floor.
Right around us, all of the rocks that we see used to be part of an ancient seabed. The limestones were part of the continental shelf. The shales were part of the deeper ocean waters, but it was all underwater.
Long before the Rockies formed, the west coast of North America was covered by a shallow sea. Over millions of years, clay, mud, and gravel settled on this coastal shelf, trapping and fossilizing tens of thousands of sea creatures. Layers of sediment solidified into rock up to 12 miles thick. The rock layers in this cliff are made from sediment laid down over 8,000 years. Today, these fossils are 1.5 miles above sea level. But once they were buried 6 miles under other layers of rock.
At their deepest point, these fossils were buried over 10 kilometers under the Earth's crust. And since then, they've been thrust up to over 2 kilometers up into the air, where we actually find them now.
This ancient rock formed offshore, 400 miles west of here. So what could have driven this ancient seafloor so far inland? And what pushed it up almost 8 miles? A force powerful enough to transform a flat ocean floor into massive mountains. Subduction. 180 million years ago, the North American plate was moving west, driven by the breakup of Pangaea, and the Pacific Ocean plate was heading east. The two colossal plates met head-on. In this clash of the titans, the denser Pacific Ocean plate was forced down beneath the more buoyant North American plate. Professor John Geisman from the University of New Mexico demonstrates.
What I'm going to do is simply tap on one of the sides, and I'm going to create an instability. Now we have oil starting to migrate, move its way over the top of the CD. Ah, voila, it's happening all by itself. I don't have to nudge it anymore. You see the oil moving its way across the CD like so, and the CD itself is going to begin to move like so into the oil, and the subduction process is completed. It's subducted into the interior of our planet, if you will. And it's a runaway process. You can't stop it.
On top of the subducting Pacific plate sat offshore islands. As the plate was pushed eastward, it carried these islands like a conveyor belt. One particularly large island reached the junction of the two plates and coast of North America, but it was too large and buoyant to be pushed down into the mantle. Instead, it slammed into the continental shelf on the western edge of the continent. The seabed was shoved eastward. It slowly folded up like a crumpled carpet. The fossils of the Burgess Shale were pushed thousands of feet into the air and miles inland. Geologist and author Ben Gadd has spent 30 years studying the Rockies here in British Columbia.
One way to imagine this whole pushing and shoving business is to do it on your hands. So you have the bony part of your hand, and then you have the skin over the top, right? So imagine that the bony part is the continental plate, and on top of that, you have all the sedimentary layers, right? That's the skin. So when the big push and shove comes, you have the skin being pushed along the bony layer, and as it gets pushed along, it wrinkles up. That's a good analogy for how the Rockies were formed. The older I get, the better this works for some reason.
Over millions of years, the plate collision forced up the northern Rockies. When the force of this collision lost its power, the first wave of mountain building came to an end. But that's not the end of the story. 80 million years after the first block of land hit the coast, a second one slammed into its back. It bulldozed everything eastward and upward. Layer after layer of rock was shoved higher and higher. First into hills, and then into mountains. Gentle folds of rock evolved into the mighty Rockies. Today, these slabs of land, called terrains, make up British Columbia. As they continued to rise, the Rockies were continually sculpted by the momentous force of the elements. Even as they were pushed up, erosion was starting to tear them down. The Canadian Rockies. Jagged peaks, steep cliffs, and razor-sharp ridges, carved from the sedimentary rock of an ancient seabed. Despite being caught in a mighty plate collision and thrust up into towering peaks, the layers of rock in these mountains still lie almost horizontally. This provides a clue about how they rose up. As the blocks of land drove into the coast of North America, slabs of sedimentary rock were pressurized and folded so much that they snapped. Broken sheets of rock, up to a mile thick, shunted forwards and slid over each other again and again, in a process scientists call thrust faulting.
So the rock has actually been folded to the point where it can't be folded anymore. And at that point, the upper part of the fold will literally break and start sliding along. That's what we call a thrust fault. And it's a classic kind of fault for the Canadian Rockies.
Sedimentary rock forms when younger layers of sediment settle on top of older layers. But here in the Rockies, layers of different ages are jumbled up. Thrust faulting pushed older layers of sedimentary rock up and over younger layers.
Suppose that we think of this book as being a continuation of the layered rock that we see here. Now, in a thrust fault, what happens is this part will break up and it will slide along like this, and it can go rather a long way until eventually it stops. So now we have layers that were down here pushed up over these layers. Old rock pushed up and over younger rock.
In this laboratory sandbox, the layers of colored sand represent layers of sedimentary rock. As the sand pushes eastward to the right, thrust faults form, one in front of the other. Thrust faulting pushes older rock layers above younger to create the distinctive sawtooth ranges of the northern Rockies. These mountains first emerged 140 million years ago. Thrust faulting first built the western ranges, and then crept eastward, forming a new range further inland. 120 million years ago, the main ranges appeared. And then even further east, the front ranges, 85 million years ago. Thrust faulting began to slow down until eventually, 50 million years ago, it stopped. At Mount Yamnuska, the mountains and the foothills meet. Beyond lie the flat plains of Alberta and Montana. Immense forces pushed an ancient seabed thousands of feet into the air. But a very different force sculpted it into these striking peaks. Erosion. Evidence of erosion's power is strewn all over the mountainside. Piles of broken shale and heaps of ash-colored sediment called scree.
erosion has been at least as important as the mountain building itself. It's the mountain building process, the uppiling, that gives you the elevation to give you the height of the landscape, but then the landscape itself is carved downward differentially. So erosion is very important. It actually gives us the landscape we see.
Erosion is so powerful that it has scraped up to 2 miles of solid rock off the top of these mountain peaks. And the main force of erosion is water.
Water loosens materials, sends it downhill. Water dissolves minerals. Water freezes and breaks up the rocks.
The northern Rockies are made of sedimentary rock like sandstone, shale, and limestone. Relatively soft and soluble, these are easy prey for erosion. And here in Canada, water's erosive power takes on a new dimension. In this cold climate, snowfall freezes and compacts to form enormous sheets of ice, glaciers. The glaciers here creep forward at 50 feet per year. On a geologic timescale, this is fast. Glaciers pick up and carry loose rocks and boulders, which scour and scratch the rock beneath them. Like giant ice cream scoops, glaciers gouge out distinctive U-shaped valleys. And when they melt, they leave behind deep gorges and steep-sided peaks. Erosion has worn down these rocks over millions of years. But the Rockies are fighting back. While erosion attacks their summits, deep below ground, the mountains are still growing. Look at the Rockies, and it's like seeing the tip of an iceberg. Mountains have roots, which can be 5 or 6 times deeper than their height. This mountain stands over 2 miles high, but its hidden root could extend 13 miles underground. These roots are the Rockies' secret defense against erosion. Structural geologist Carl Karlstrom from the University of New Mexico demonstrates using blocks of ice. The red and green ice layers represent the mountains above ground, and the white ice their roots below ground.
Mountains are not static things. The Earth's surface is continually being reshaped by erosion, by rivers, by glaciers that tear the mountains down. So let's imagine I'm eroding the mountains now, and I'll just pull one of the blocks off. The overall surface has gone down. The continent has gotten thinner, its roots come up, and now this rock, which was deep in the earth a minute ago, underneath the green layer, has come to the surface. That's called rock uplift. So I guess I'll erode off the pink layer too. We're back down to a continent without a major mountain belt, something like the eastern part of North America.
When the heavy weight of the mountain is eroded away, the root rebounds upward. This process means that the Rockies are constantly topped up from beneath. In Canada, thrust faulting and erosion have shaped the mountains. But as we travel south, this distinctive landscape is about to change. Just south of the U.S. border in the state of Montana, a new rock appears among the Rockies: granite. This is the first clue that the mountains of the American Rockies are radically different. On our journey south along the Rocky Mountains, we're entering a very different landscape. From Montana southward, the Rockies are made from ancient granite, 1.7 billion years old. Granite makes up much of the deepest part of the continental crust. That's why geologists call this rock the basement. The Canadian Rockies are built from sedimentary rocks piled up on top of the continental foundations. So why does granite suddenly appear here in the American Rockies? But there's an even greater puzzle. Mountains usually form close to plate boundaries, but the Southern Rockies sit a long way from the plate margin. The Front Range in Colorado is 1,000 miles from where the Pacific and North American plates actually meet. Geologists have come up with an explanation. They believe that the subducting Pacific Ocean plate is responsible. Ocean crust had been pushed deep into the mantle beneath North America for 100 million years when something unusual happened. 70 million years ago, the Pacific Ocean plate started to subduct at a shallower angle. Instead of plummeting steeply, it sliced beneath North America horizontally. This change had dramatic consequences.
The big oceanic plate in the Pacific didn't go deep down, it went in shallow like a spatula under a pizza. So something happened 68 million years ago over in California. That plate drives under North America, but instead of diving deeply, it comes in shallow, and 1,000 miles away from the coast, up from the ground, sprout the Rocky Mountains.
For millions of years, the ocean plate scraped along the underside of North America. It created friction, breaking up the basement granite of the North American plate and punching it upward. Structural geologist Carl Karlstrom demonstrates.
Because it was at a shallower angle beneath North America, it was scraping along the base of North America. When that happens, it puts the plate under compression like this, because it's being both pushed at the end and scraped along at the bottom. So it squeezes, pushes up the mountains, and it transferred this mountain building from the edge to great distance from the plate margin.
The shallow angle trajectory of the Pacific Ocean plate explains why these mountains formed so far inland. And it also explains the presence of granite. Thrust up through layers of sedimentary rock, the broken granite became the Rocky Mountains of the South. Red Rocks Park, Denver, Colorado. A landscape forged by granite uplift. Kirk Johnson demonstrates how these granite peaks punched up through the layers of red rock around them.
I'm going to use my assistants, Veronica and Ian, to help me explain how the Rocky Mountains in Colorado formed. Imagine, if you will, that Veronica and Ian are composed of 1.7 billion-year-old metamorphic rocks, the basement rock of Colorado.
Before the mountains grew, layers of sedimentary rock covered the granite.
And then about 68 million years ago, the mountain where Ian is starts to break and lift up and move up. So you see the uplift forming. And what's happening is that layer of sediments being deformed and bent. And these are the flat irons at Red Rocks. As the mountain comes up, overlying sediments are eroded off and deposited into the adjacent basin. And eventually, Ian's granitic back is exposed as the core of the Rocky Mountains. Veronica remains deeply buried beneath Denver, still covered with deep sediments, and the sediments eroded off the uplifting Rocky Mountains.
Johnson is investigating exactly when these events took place. He focuses on the Colorado Rockies Front Range, which runs 350 miles between North and South Colorado. Dating the Rockies requires real detective work. And like all detective work, you get clues by digging up dirt.
Yeah, so it's sort of counterintuitive. To understand mountains, you don't look at the mountains necessarily, you look at the debris from those mountains. So just like a detective would go through a criminal's garbage can. The basin adjacent to the mountain range is sort of a garbage can of the adjacent mountains. The mountain goes up, it sheds all its garbage off to the side, in this case sedimentary rock and fossils, volcanic ash beds, layers of lava. We can look at that garbage and reconstruct the chronology of the uplifting mountain range.
Today, this debris forms layers of sediment 10,000 feet thick beneath the city of Denver. In their mission to date these massive peaks, Johnson and his colleagues search for the tiniest clues, like fossilized leaves and pollen. For Doug Nichols from the Denver Museum of Nature and Science, these microscopic grains of pollen provide a valuable lead.
Pollen can be used to date the uplift of mountains because plants that were living at the time the mountains were coming up were shedding their pollen, which was becoming incorporated into sediment, which was being eroded from those same mountains. And I'm looking for the particular species of pollen that can tell me the age of the sample.
Each sample of sediment can contain thousands of fossilized pollen particles. Nichols examines a single grain. Every plant genus has distinctive shaped pollen. So by identifying the species of plant and its age, Nichols can start to date the exact uplift of Colorado's Rockies.
We pretty well understand that the uplift began 65 to 70 million years ago because we find distinctive kinds of pollen produced by plants that only lived 65 to 70 million years ago.
Sometime during this 5 million year period, Colorado's Rockies began to rise. But geologists can narrow this window even further, thanks to one of the most catastrophic events in history. $65.5 million years ago, an asteroid smashed into the Earth. It wiped out the dinosaurs and left a distinctive line in the sediments by Colorado's Rocky Mountains. This pale yellow layer in the rock contains the remains of the huge asteroid. Because it's sandwiched between layers of debris that eroded off the Rockies, we know that the Rockies must have been up and eroding at the time of impact, 65.5 million years ago. Kirk Johnson specializes in dating fossilized leaves. He uses them to date the Rockies' birth even more precisely. Geologists know that 69 million years ago, Colorado was covered by a shallow sea. But Johnson's fossil leaves show that just a million years later, there were plants here. Johnson combines his findings with Nichols' pollen evidence to come up with a million-year window during which the Colorado Rockies must have emerged. And compared with the northern Rockies, these mountains grew up fast.
We know that 69 million years ago, Colorado was covered by a shallow sea. We know that at 68 million years ago, the Rocky Mountains were up. So sometime in that 1 million period, 1 million years, the Rocky Mountains came up. It may have taken all the 1 million years. It may have happened in 200,000 years. We don't know that yet, but we're working on that particular question.
Although Johnson's team can't yet say how quickly the mountains grew, they are certain of one thing. 68 million years ago, the American Rockies had arrived. As we continue south through the Rockies, the landscape evolves once again. 35 million years ago, at the southern tip of the mountain chain, volcanoes appeared among the peaks, triggered by changes deep beneath America. A new explosive era had begun. As we travel south 2,000 miles through the Rockies and forward through their 200 million year history, we reach Albuquerque, New Mexico. Here, a dramatic change deep beneath America triggered the most explosive phase in the evolution of the Rockies. "70 million years ago, the subducting Pacific Ocean plate punched up huge blocks of basement granite, forming the Rockies of New Mexico. "35 million years later, the Pacific Ocean plate began to peel away from the underside of the North American continent. As the ocean plate sunk deeper, warm mantle came into contact with the underside of the North American plate, right underneath parts of the southern Rocky Mountains. Just as the burner on a hot air balloon makes the air less dense, causing the balloon to float upward through the cooler air around it, so warm, buoyant mantle rose up through the cooler, denser mantle beneath the mountains. Carl Karlstrom thinks that this caused the Rockies to grow even taller.
Well, let's think about uplift of mountains in the context of this analogy of a hot air balloon. We're floating high because we're more buoyant than the air around us. And if we want to go up, actually get still higher, we'll just turn on the burner and fire it up, and then the air becomes lighter within the balloon, causing a dynamic or an active uplift. And we can think of that in the context of mountains as if an upwelling of warm and buoyant mantle is actually pushing up the mountains.
But it's not just the mountains that were affected. The upwelling mantle also stretched the crust above. This sandbox simulation demonstrates the stretching process. As the continent pulled apart, the crust thinned and fractured. An immense crevice, called the Rio Grande Rift, opened up in the heart of the Rockies. In parts of the southern Rockies, the crust is over 30 miles thick, but in places beneath the rift, it's just 17 miles thick. This thin crust triggered something dramatic. Under immense pressure from rising heat in the mantle, it gave way. Red-hot magma blasted out onto the New Mexico landscape. And volcanoes punctured the Rio Grande Rift. Scientists believe that hot magma has surged up from the mantle many times over the past 35 million years. These surges led to renewed volcanism in the Rio Grande Rift. But this is not ancient history. The last eruption, just 1,500 years ago, flooded New Mexico with a river of molten lava 44 miles long. Could such recent eruptions mean that hot magma is ballooning beneath Earth's surface today? Could the Rockies of New Mexico still be on the rise? Laura Crossi, a geologist at the University of New Mexico, is on a mission to find out. Working with Carl Karlstrom, Crossi is focusing on a fault where the Rio Grande Rift meets the Rockies. Here, hot springs bubble up to the surface from deep below. Gases in the water can provide a clue to the activity in the mantle.
This point along this fault is a place where these fluids are finding their way to the surface because of the extension, the tectonic activity. We're able to come here and have a window into that deep, deep world, all the way to the mantle.
Beneath Earth's surface, gases are under immense pressure and dissolve in water. When they reach the surface, they escape as bubbles. Analyzing samples of the gas bubbles, Crossie discovers carbon dioxide and traces of helium-3. Carbon dioxide and helium-3 are both byproducts of activity in the mantle. Their presence indicates that deep beneath the surface, rock in the mantle is melting and on the move. Like a rising hot air balloon, hot, buoyant magma is slowly surging up beneath both the rift and the Rockies. This is evidence that here in New Mexico, the Rocky Mountains are far from dead. They could still be growing, thrust higher by rising mantle. Karlstrom believes that in the future, there will be a wider rift and taller, more spectacular Rockies.
I think portions of the Rocky Mountains are going up dynamically, and that they are getting higher, and the Rockies are getting higher, and certainly in the million-year time frame, we will have more interesting, higher, and more rugged mountains, I would predict.
Having investigated their past, geologists are now looking to their future, and it's bleak. The Rockies are doomed, and North America's destiny hangs in the balance. On this journey through the Rocky Mountains' 200-million-year history, we've witnessed their dramatic birth and examined their complex evolution. Now we turn to their uncertain future, a future that goes hand in hand with the fate of the whole North American continent. This is the Columbia Icefield in Alberta, Canada, where geologists are already seeing how the mountains are changing. Within 100 years, it could look something like this. Human activity is altering the course of geological history. Increasing global temperatures are taking their toll on the mountain's glaciers. They're melting. Brian Luckman from the University of Western Ontario wants to know how fast. During the winter, glaciers grow. An advancing glacier pushes a pile of eroded rubble ahead of itself, called a moraine. When the glacier shrinks back in summer, it leaves behind this pile of debris in its wake. It's a telltale sign that the glacier is melting away.
Because the glacier over time is retreating continuously, then what you have left are a series of these annual moraine ridges, which mark the furthest point of advance during the previous winter.
Luckman walks between the moraines, using GPS to map the distance between each one. The greater the distance between them, the faster the glacier is melting.
Glaciers are one of the most effective ways to demonstrate to people that the climate is changing. You've only got to come here twice or look at some of the older photographs to realize something radically is changing.
These two photographs of the 3.5-mile-long Athabasca Glacier show how far it has retreated over the past 30 years. And these photos of the Grinnell Glacier in Montana show that America's glaciers are disappearing as well. One day, the glaciers that have shaped these steep-sided peaks and U-shaped valleys will disappear. But water erosion will continue to sculpt these mountains, beating them down and softening their jagged edges.
The future of the Rockies is that they're eroding at the rate of about 0.06 of a millimeter per year. This is based on taking a sample of river water, measuring the sediment in it, and seeing how fast the Rockies are being carried off to the sea.
The relentless force of erosion has sealed the fate of the Rocky Mountains since they first began to rise. One day, they will erode away to nothing.
The Rockies that we see today, the beautiful mountains, why tourists come here, why it's just one of the most dramatic places on the earth, they're eroding away. And so if we look at all the rivers draining off of them, they're full of silt and sand, and that is our Rockies slowly bleeding to death.
The Rockies will eventually dissolve away. But far in the distant future, there could be a final devastating twist to their story. A continent ripped in two. The future of the Rocky Mountains is inevitable. Thanks to the relentless force of erosion, they will one day disappear. But they will leave a legacy. The Rio Grande Rift. A great tear in the Earth's crust that could one day split North America in two. Geologist Mizumi Roy and her colleague Nicholas George, both from the University of New Mexico, are taking part in an ambitious 5-year project. Its aim? To monitor the widening of the Rio Grande Rift. The team is setting up GPS stations along the length of the rift, like this one in remote New Mexico, 3 hours from Albuquerque. The GPS receivers are buried in the bedrock to a depth of around 5 feet. When the Earth moves, the receivers move too. Roy explains.
If you have 2 GPS stations, then you have information about relative motion along a line that connects the 2 stations.
A network of GPS stations allows the team to build up a much more detailed map of the rift's motions.
By looking at the difference between the coordinates between the GPS stations through time, we get a good idea of the relative motion between each of these stations.
The team has set up 24 GPS stations along the Rio Grande Rift. It's early days, but the team expects to find that the rift is widening between 0.5 and 2 millimeters every year. It's a very slow process. But little by little, the continent is being unzipped.
The Rio Grande Rift is a rift system that's causing a continent to split. And if this process continues for tens of millions of years, you could eventually rift the North American continent apart.
There's a lot of indications that there's some action happening. Maybe some more is in the future for the Rocky Mountains, and another few million years and there'll be greater tales to tell of active tectonism further to the north, where this Rio Grande Rift is trying to work its way and crack the continent. I think it'll be unsuccessful in that attempt, but it's giving it a good show.
The story of the Rocky Mountains began with the birth of the North American continent. And it could end with its death. One day, the Rio Grande Rift may split a continent. North America might become East and West America. But all this is hundreds of millions of years into the uncertain future. Today, the iconic Rockies are in their prime. The mountains that divide a continent unite us all in admiration. Dramatic and resilient, they will remain the backbone of North America for millions of years to come.
A split second, the Big Bang, and the whole universe was born.
In the blink of an eye, literally, so much can happen that it would blow your mind.
How did we get here? And what is the universe made of?
The secret of creation, the secret of everything is locked in that first second.
Technology stands on the brink of revealing what happened in the most important second of all time. In the beginning, there is nothing. No matter, no energy, not even empty space, because space itself doesn't exist. No time passes, because there's no such thing as time. From nowhere appears a fireball smaller than an atom. 10 trillion times hotter than the core of the sun. Everything that will become the universe explodes from a point millions of times smaller than a pinprick. Time begins. In 1 second, the blueprint for the entire cosmos is written. How it happened is the biggest mystery of all. Professor Lawrence Krauss has devoted his career to studying the first second after the Big Bang.
If we want to really understand our place in the universe, we have to go back to the very beginning and understand how it all came together.
Looking back to the instant of creation is a new idea. The theory of the Big Bang is widely accepted, but the concept is less than a century old.
But one of the things we have to put in perspective is how recent our understanding of the universe is. 80 years ago, the conventional wisdom in science was that the universe was static and eternal, had been around forever.
But this changes in 1929. At California's Mount Wilson Observatory, Edwin Hubble studies the light from galaxies. He observes that the farther the galaxy, the longer the wavelength of light it emits. Light waves stretch the more they travel, and stretching changes their wavelength. The same principle applies to sound waves. As a train approaches, the whistle's pitch rises. When it passes, the pitch lowers. As the train recedes, each sound wave has to travel farther than the last to reach your ear. The sound waves stretch, lowering the pitch. Something similar happens with light waves. If a galaxy is moving away from us, its light waves stretch, becoming longer and redder. It's called red shifting.
When we look at visible light, there's red at one end of the spectrum and blue at the other. Red radiation is the long wavelength radiation of visible light, whereas blue radiation is the short wavelengths. And as we look at the universe, we see the radiation from distant stars literally stretching so that the light gets redder. And the farther away we look, the redder the light is.
Galaxies around us have shifted to this red light.
We look out in all directions at distant galaxies, they're all moving away from us.
Nearly all galaxies are receding at 1 million miles an hour. If galaxies are speeding away from each other, at some point, they must have all been together. The universe is expanding outward from a single point. It's the first evidence that the universe had a beginning. Hubble's findings lead to a radical concept: the Big Bang Theory. Scientists believe that in the first second after the Big Bang, the building blocks were created for every star and planet in the cosmos. To prove it, they first need a new way to tell time.
We are thinking of fractions of time smaller than we think about in any other area of human activity, and smaller fractions of time than a race car or a sprinter or anything else. And what we've learned is that more can happen in a fraction of a second, in a blink of an eye, than you can imagine. It would just blow your mind.
Hours, minutes, and seconds are the basis of modern life. But events after the Big Bang happen in fragments of time far smaller than a second. To analyze what happens, scientists use a new measure of time called Planck time. 1 Planck time equals 10 to the minus 43 seconds. That's a decimal point, 42 zeros, and then a 1. It's an unimaginably small amount of time. Yet in this first tiny beat of Planck time, something happens that shapes the next 13.7 billion years. Out of the fireball, the 4 fundamental forces of nature form. Those forces underpin everything around us. Gravity is the reason stars and planets form. It rules the moon and tides and keeps us on the ground. Electromagnetism lights our cities, connects our phones, and runs our computers. And the 2 nuclear forces, strong and weak, bind the particles that make up our bodies and power the furnace of our sun. We're here because in the first second after the Big Bang, the 4 forces are created. Without them, the universe would be a featureless fog of radiation.
If there were no forces, nothing would happen. There'd be no television. There'd be no sports. There'd be no love, no hate, no human tragedy, all the things that make life worth living.
But in the first beat of Planck time, the 4 forces are still rolled into a single superforce. Gravity, nuclear, and electromagnetic forces have not yet divided. Physicist Michio Kaku studies how the forces split apart.
I like to think of it as a crystal, a beautiful symmetrical crystal, all the forces unified in their elegant simplicity at the beginning of time.
As our cosmic clock takes one more tick of Planck time, the tiny fireball universe expands. The 4 forces start to break apart. It's like rapidly cooling a super hot crystal. Cracks form.
It began to shatter into 4 pieces. The first piece to break off was gravity. Then the nuclear forces began to split off. And finally, we have this fragmented jewel of what used to be the superforce.
Those 4 fragments are still at work. Gravity keeps Earth in orbit. Nuclear forces make sunshine. And electromagnetic radiation, the light that bathes our planet. We're just fractions of a second into our journey, and already the foundations of our world are forming. The fireball universe. Still smaller than an atom, and 1,000 trillion degrees. To discover how the universe expands, scientists use telescopes so powerful they can see the past. When astrophysicist David Spergel looks up, he sees history.
As we look out in space, we look back in time. Light travels at a finite speed. So the light we see from the sun takes about 8 minutes to get here. We see the sun not as it is, but as it was 8 minutes ago. We look out the night sky, we see the nearby stars. They might be 10 or 20 light years away. We see them as they were 10 or 20 years ago.
The Big Bang was so powerful and so hot, remnants of that heat still survive. The heat began as super hot X-ray radiation. As it stretched and cooled, it became visible light, shifting from blue to red. then becoming microwaves, and finally radio waves. This faint radiation shines down on Earth all the time. It's called cosmic microwave background radiation, or CMB.
The cosmic microwave background is the echo of creation itself. It's the embers, the afterglow of the original shock wave that created the universe. If we had microwave eyes that could see microwave radiation, then every night we would see the Big Bang coming out. Looking at the heavens, we would actually see an explosion.
More than 13 billion years later, we have a way to see this cosmic glow with the naked eye.
You take your TV set, switch it between channels. A couple percent of the static that you see on your TV screen is radiation from the Big Bang.
This cosmic radiation is a direct connection to the Big Bang. It also reveals the universe entered a new phase, less than a trillionth of a second after its creation. Cosmic radiation is the key to discovering what happens next. A few beats of Planck time tick by on our cosmic clock, and the fireball universe is transformed. One instant, the universe is billions of times smaller than an atom. The next, it inflates to the size of a baseball, growing more in this moment than in all the 13.7 billion years to come. Scientists call this rapid expansion inflation. And the evidence survives in the cosmic radiation left over from the Big Bang. Like static on your television, this cosmic radiation seems so constant and so even, it presents scientists with a puzzle.
When we measure the cosmic microwave background in that direction, its temperature is identical to its temperature in that direction. It's the same everywhere.
The only explanation is the universe inflates countless times faster than the speed of light. Inflation expands the fireball universe evenly, like a balloon blowing up, with a phenomenal breath of energy.
I try and imagine compressing a spring. I push it closer and closer and closer together so it's smaller and smaller and smaller, and I've stored a tremendous amount of energy in that spring, and when I let it go, it bursts out. And that stored energy drove an exponential expansion of space.
But if the entire universe is uniform from the first second after the Big Bang onward, how did the galaxies form? Planets and stars begin as clusters of particles. Over time, these particles of matter clump together under the force of gravity to form a dense mass. Earth began as a ball of particles that clumped together through friction and gravity. The sun that sustains life on Earth started out as a cloud of gas and dust. How did these clusters form in the first place? The early universe should be lumpy, not even. To link the formation of stars and planets all the way back to the first second after the Big Bang, NASA scientists like David Spergel developed the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite mission to measure the temperature of cosmic radiation in more detail than ever before.
While this radiation is everywhere, it's very faint. And to observe it in great detail across the whole sky, you want to get away from the Earth and any interfering sources of radiation.
7, igniters armed, green board, 5, 4...
NASA launches the probe in 2001.
Main engine start and liftoff of the Delta II rocket with the MAP spacecraft, exploring the past and future of our universe.
It could produce the best ever snapshot of the universe in its first second.
The launch was incredibly exciting, tense, but exciting moment to see it go up and then realize it was working.
WMAP sits 1 million miles from Earth. It's so sensitive, it can measure the temperature of cosmic radiation within a millionth of a degree. For 5 years, WMAP analyzes the sky in minute detail.
It sits there with the Earth and Sun always behind it, staring out into space. The satellite's spinning very rapidly. It covers about a third of the sky every hour, spinning and making maps of the leftover radiation.
WMAP tracks the Earth as it orbits the Sun and scans the temperature of the whole sky. It generates detailed temperature maps like this one, and it reveals something remarkable. The blue and red patches on this map of the entire sky are tiny ripples in temperature.
The little blue regions represent regions that are a few tens of thousands of degrees colder. Red regions are a little bit hotter, so you're seeing tiny variations in temperature across the sky.
WMAP looks back over 13 billion years. As the universe evolves, these tiny ripples develop into clusters of particles that get bigger and bigger under the force of gravity, becoming just dense enough to trigger stars and galaxies to form.
I mean, it really was what I think we all dream of when we go into science. Looking at things that no one's looked at before, learning really exciting things about fundamental questions. Questions like, what's the universe made of? What happened in its first moments?
This is a map of how the universe looked in the first second after the Big Bang. The template for today's vast cosmos.
When the picture of the cosmic microwave background radiation first came out, the press said, "Ah, the face of God." Well, let's be real. It's not the face of God. What it really is a baby picture of the infant universe. So the discovery of the cosmic microwave background radiation ranks as one of the greatest discoveries in all of science.
Less than a trillionth of a second after the Big Bang, the fireball universe rapidly expands. Now an ultra-hot globe big enough to sit in the palm of your hand, the universe is seething with energy and radiation. But as the palm-sized universe expands and cools, something new starts to form. Only a fraction of a second after the Big Bang, and the destiny of the universe is already mapped out. The sun burns because of forces forged more than 13 billion years ago. The stars and planets form from the way the universe rapidly expands. Science can trace everything we see today back to the first second of creation. But we're here because of what happens in the next few beats of Planck time. The universe is flooded with the building blocks of matter. So far on our cosmic clock, the early universe is nothing but energy. How did pure energy turn into matter? Everything around you is made of matter. What you're sitting on, the air you breathe, the whole planet is made of matter, and matter is made of atoms. And in the first second after the Big Bang, the ingredients for atoms are created. How matter appeared mystified scientists until 1905, when Albert Einstein comes up with our most famous equation. E equals mc squared. Einstein's equation tells us that energy, E, and mass, m, are different forms of the same thing. Matter and energy are interchangeable. Some scientists later used this equation to create the most destructive weapon in history, the atomic bomb. It offers a clue to what happened in the first second. In a nuclear explosion, Particles of matter are ripped apart to produce an enormous amount of energy. During the Big Bang, the exact opposite happens. An enormous amount of energy turns into matter. Einstein's equation prompts a conclusion. As the baby universe expands and cools, the pure energy of the Big Bang converts into the particles of matter that make us. We're only a fragment of a second into our journey. The first particles of matter appear. The universe is 1,000,000 times hotter than at the core of the sun, still far too hot for particles of matter to bond and form atoms. Scientists face a puzzle. What is this early state of matter like? And how does it become the protons and neutrons that form every atom in the universe?
Atoms were impossible. Think of putting an ice cube in a steam bath. The ice cube would melt immediately. You cannot have ice cubes in a steam bath.
You can see the proof in a block of ice. When water is cold enough, it's a solid. Warm it, and you get a liquid. Heat liquid water, and it boils away into a gas, water vapor. Superheat the gas, and the energy pumped in rips the atoms apart. Likewise, the universe in the first second is so hot, only the building blocks of atoms can exist.
If you were to journey into the early seconds of the universe, literally you would disintegrate. You would literally fall apart, and even the debris, the nuclei of your bodies, they too would fly apart into subatomic particles. There would be nothing left of your body.
There's only one way to see these super hot building blocks of matter in the first second after the Big Bang. Scientists must recreate conditions of the Big Bang itself.
The inside of a star is measured in tens of millions of degrees, but the Big Bang was measured in trillions upon trillions of degrees. So we have no way to simulate the instant of creation other than with a particle accelerator. By slamming protons into other protons, we can create temperatures not seen since the beginning of the universe itself. So particle accelerators are the only game in town when you talk about simulating Genesis.
This is Brookhaven National Laboratory in Long Island, home to the Relativistic Heavy Ion Collider, or RHIC, a 2.5-mile ring designed to smash the nuclei of gold atoms at nearly the speed of light.
With the particle accelerator, you slam subatomic particles together. As a consequence, we get a tremendous shower of debris, and then we want to make sense out of it. We want to know what's inside that collision.
The energy of the collision is colossal. On a small scale, it reproduces the embryonic universe in the first second. How? By ripping nuclei into the protons and neutrons they're made from. The energy is even enough to rip the protons and neutrons apart. Inside, scientists discover the building blocks of matter, tiny particles called quarks. But they're so small and move so fast, they're hard to track. If scientists can figure out how quarks behave, they'll unlock the secret of matter itself. What they find could revolutionize medicine and relaunch the space program. The project starts in 2000. Colliding nuclei creates a chaotic spray of particles. It takes 5 years to analyze the data. The results come in 2005. They're shocking.
We were expecting to find a gas when we slam gold nuclei into each other. So the shock was, it wasn't a gas at all. We found that it's more like a liquid. So this came quite a shock, because now when we begin to simulate the early universe, we have to get rid of this mental picture of a gas of subatomic particles. Now we know it's more like a liquid, literally like a soup.
When matter first appears in the universe, the quarks are so dense and so energized that the entire universe is like a liquid. The universe went from a glowing ball of energy to quark soup in less than a blink of an eye. The liquid universe is hot, dense, and violent, flooded with tiny particles in constant vigorous interaction. As our cosmic clock reaches a millionth of a second, the universe continues to expand and cool. It grows from the size of a baseball to the size of our solar system. Matter has materialized from pure energy. Without matter, none of us would be here. And in that first second, that very nearly happens. Something comes close to destroying all matter in the universe. Armageddon is brewing. A split second after the Big Bang, and the universe is flooded with the building blocks of atoms. These tiny particles of matter must survive in a battleground. Everything around us is made of matter formed from the energy released by the Big Bang. Every molecule, every atom, every quark. How we end up with a universe that consists of so much matter is one of our biggest questions. The particle accelerator may reveal the answer. When the first second is recreated, two types of matter are produced in equal parts. One is the type of matter we see around us. The other is its opposite, antimatter. Dr. Tara Shears explains they're two sides of the same coin.
This apple is made of matter. We know that every matter particle in the universe has an antimatter partner that was created in the Big Bang. Now, antimatter looks similar to normal matter, but not quite. In fact, it looks like the mirror reflection of matter. So an anti-apple looks like this.
If the universe was made of antimatter, it would essentially look identical to how it looks today. You and I would be made of antimatter, and anti-lovers would sit in anti-cars looking up at an anti-moon at night making anti-love, and it would be largely the same.
But matter and antimatter are mortal enemies. They can't coexist.
When we have a matter particle meeting an antimatter particle of the same type, then they annihilate, they explode together, they destroy each other. All the energy that the matter and antimatter particle have goes into one large explosion of huge, tremendous energy.
Fractions of a second after the Big Bang and the future of the universe is at stake, matter and antimatter are locked in a battle to the death. A millionth of a second after the Big Bang, and a battle rages. When matter and antimatter clash, the result is explosive. Just one apple-sized clump of matter hitting its antimatter equivalent would release as much energy as a 10-megaton nuclear bomb.
If you could go back to the really early universe just after the Big Bang, you'd find yourself in this seething mass of matter and antimatter annihilating each other. You'd find yourself in the middle of this cosmic battle between both sides, caught in the crossfire, if you like.
With all the particles in a super-dense liquid state, matter and antimatter quickly meet and destroy each other. Since they're created in equal numbers, and every matter particle that hits an antiparticle is annihilated, all matter should be destroyed as soon as it's created.
All the matter would have eventually found the antimatter, and they would have annihilated, producing pure radiation. And we'd now have a universe. I was going to say we'd now be living in a universe of pure radiation, but we wouldn't be living in such a universe because we wouldn't be here. There'd be nothing but radiation.
But the universe is full of matter. How did it defeat antimatter? It's one of science's great mysteries. One theory is that antimatter is less stable and decays more quickly, creating a tiny imbalance between matter and antimatter. This tiny imbalance eventually allows matter to overwhelm antimatter. Whatever the truth, something happens just after the Big Bang that tips the balance in favor of matter.
And the whole battle stopped at that point, and what was left was a very small amount of matter. And it's that small amount of matter that makes the universe that we live in now. That means that we're the leftovers of this battle. We're the dregs. We're what's left when everybody else had finished.
The dregs go on to form everything around us. From the ground beneath our feet to the most distant galaxy. As the cosmic clock nears the end of the first second, nature's four forces have split off from the single superforce. The winner of the matter and antimatter war has been decided, and the subtle ripples in temperature that stretch across the universe mean that over the next billion years, gravity gathers clumps of matter to form galaxies. But one mystery remains, and it's a big one. We know how the building blocks of matter form, but we don't know what gives everything in the universe substance. We know so much about the first second, but a piece of the puzzle is missing. What gives everything in the universe mass? Mass makes it tough to get something moving, and makes it hard to stop. When we're pulled down to Earth, gravity is acting on our mass. On the Moon, gravity is weaker, so astronauts move slower, but their mass is the same as back on Earth. Even if an object weighs nothing, it still has mass. Something must have been created in the first second to give particles mass, but scientists haven't found it.
We have this hole. We have this missing piece. The centerpiece of this whole picture is what happened during that first second of creation. If you know that, then you can, quote, read the mind of God, as Albert Einstein used to say.
Mass is the very backbone of life.
If there were no mass, the universe would consist entirely of radiation, and nothing could bind together to form objects like you or I, or any of the things that appears to make the universe interesting. It would be a diffuse universe full of radiation, but very, very boring.
Discover how mass develops in the first second, and you uncover the root of life. If scientists can't find what gives particles their mass, that first second will remain an enigma. Our journey is almost finished, but a piece of the puzzle is missing, and it stumps scientists for decades. Then in 1964, at Britain's University of Edinburgh, physicist Peter Higgs comes up with a groundbreaking theory. He suggests an invisible force field sweeps across the universe in the first second, giving particles their mass. It's become known as the Higgs field. When particles interact with it, they gain mass.
For example, if I take a car and that's run out of gas and I push it on the road, eventually I can push it and I can move it along. But if it runs into the mud, if I try and push it, it will suddenly seem heavier. I can't push it as hard. It'll act as if it's heavier. Well, we think that particles have mass for a similar reason. There's this Higgs field, and some particles interact with it more strongly than others. And the particles that interacted with it less strongly are easier to push, and therefore behave as if they're lighter. The particles that interact with it more strongly are harder to move and act as if they're heavier.
Like mud, the Higgs field sticks to everything. When particles enter the field, they gain mass. The more contact with the field, the more mass they gain. Scientists believe the Higgs field is carried by its own special particle. Journalists call it the God particle. Scientists call it the Higgs boson. They think identifying this particle could reveal how we got here. The math is good, but no particle accelerator was powerful enough to find the Higgs boson. Until now. Deep beneath the countryside in Geneva, Switzerland, is mankind's most expensive experiment, the Large Hadron Collider, or LHC. The world's biggest particle accelerator and the best shot at finding the missing Higgs.
We've got to see if the Higgs particle really exists. And that's why we have to build these mammoth accelerators, to see if we can understand the mechanism responsible for the existence of everything we think of as solid and heavy in the universe today.
It cost $10 billion, took 14 years to build, and involves the work of 7,000 scientists. This year, they switch it on. On a small scale, it will recreate conditions last seen over 13.7 billion years ago. An explosion so powerful, it will echo the Big Bang itself. If it works, scientists like David Evans could solve the last mysteries of matter.
Because we're pushing the frontiers of science, we have to also push the frontiers of technology. It is, as well as probably the biggest machine in the world, it is certainly the most complex machine in the world.
Over 300 feet underground runs a 16-mile circular pipe. Inside, two beams of protons, thinner than a human hair, are accelerated to almost the speed of light, 186,000 miles per second. The LHC will smash particles together 7 times harder than any other accelerator. 300 trillion protons fly around the pipe in opposite directions and collide in the heart of enormous detectors. Lawrence Krauss inspects one of these detectors, each the size of a 5-story building.
Here we are at what's been aptly described as being one of the Gothic cathedrals of the 21st century. This monstrous structure made of thousands of tons of steel, more iron than in the Eiffel Tower, with tens of thousands of miles of wire. All of this designed by thousands of physicists from hundreds of countries, speaking dozens of different languages, with the precision of perhaps a millionth of an inch, just to detect what happens inside there.
The LHC uses 4 of these giant detectors along the beam pipe. The one they hope will find the Higgs is called Atlas. Atlas is half the length of a football field and weighs as much as a nuclear sub. It can detect 1 billion collisions per second. When the protons collide, the impact is so titanic, in a split second, it will recreate matter as it was just after the Big Bang. A shower of fundamental particles, like quarks. Somewhere in the debris, they hope to find the elusive Higgs. But finding one particle in this firestorm is like finding a speck of gold on a beach. The Higgs is so tiny and so short-lived, the detector won't see it directly. Instead, they hope to capture the trail it leaves behind, using the most high-tech cameras in the world.
When you look at a Skyrider, you see this gigantic plume of smoke, but where's the airplane? You never see the airplane. The airplane is too small to be seen. That's how we use detectors. Detectors cannot pick up the particle itself, but it can pick up the trail left over by the subatomic particle, and looking at the trail, we can determine what kind of particle it was and how fast it was moving.
The LHC will generate more data than any other instrument on the planet.
In a single second, the amount of information that's coming out of the collisions at the LHC that will be handled by these detectors is greater than the amount of information in all the libraries in all the countries in the world.
That data may hold the secret of mass, the missing piece in the universe's first second, and the doorway to the science of the future. To process all this information, the LHC uses the world's largest network of supercomputers. Even so, the search may take years to complete, but it's worth the wait. If it succeeds, the LHC could launch a new era in science. If it fails to find the Higgs and reveal how matter gets its mass, it will leave a hole in the riddle of the first second. New theories will have to be written, and more powerful experiments built.
Hey, I'm a realist. I realize that perhaps we'll find nothing. That could create a crisis in physics. It could stagnate all of physics if all of a sudden our machines are not powerful enough to unveil the next act, the next curtain, where we look at the next stage of matter and energy.
One thing they know, the LHC will take scientists closer to the Big Bang than ever before. It will reach back 13.7 billion years to recreate the very first second of the universe. The greatest second. Our cosmic clock takes its final beat of Planck time. The universe is 1 full second old. It's about 1,000 times the size of our solar system, and flooded with particles of matter, the raw material of everything around us. The universe is cool enough for the sea of quarks to bunch in threes, forming protons and neutrons. In the saga of the universe, this first chapter set the course of history.
The first second of the universe was an incredibly exciting and important time. During that first second, all the matter in the universe was made. All of the neutrons and protons were made. All the key components to make the universe today, we think were already in place. And then everything just evolved forward.
In the next few minutes, the universe cools enough for protons and neutrons to form the first atomic nucleus. 300,000 years later, appears the first atom. In hundreds of millions of years, matter clumps to form the first stars. And in 1 billion years, galaxies like the Milky Way. More than 9 billion years after the Big Bang, Earth is born. One Big Bang, one single second. The genesis of everything.
By the time you've got to the end of 1 second, the rest of cosmic history is prescribed, including, ultimately, the future of the universe.
More than 12 billion years after the Big Bang, humans evolve. A species with the intellect to ask, how did we get here? And what is the universe made of? This year, science moves closer to discovering the answer. And the secret will lie in the first epic second. Of all the world's drinking water, 1/5 is stored in one place, the Great Lakes. They're so big, they're like inland seas. So vast, they make their own weather. Without them, a large part of North America would be arid. They're filled with enough water to flood the continental United States 9 feet deep. But water levels are changing dramatically. To understand where the waters are going, you have to know where they came from and unlock the mysteries behind the Great Lakes. The Great Lakes deserve their name. They cover an area bigger than Utah and hold 5,500 cubic miles of fresh, drinkable water. The deepest of the 5 lakes, Lake Superior, is over 1,300 feet deep. Lake Michigan and Huron provide drinking water for over 10 million people in Chicago and Detroit. Between Lake Erie and Ontario is the mighty Niagara Falls. At its peak, over 40 million gallons flow over the falls every minute. It provides electricity to roughly 5 million homes. The Great Lakes are unique. But how did these 5 vast lakes form? What force was so powerful it reshaped solid rock and carved such deep depressions? Beneath a sea of water and silt, the lakes cover up the evidence of their origins. Yet on an island in Lake Erie, one clue is exposed. Kelly's Island sits on ancient rock. The rock is scarred by strange grooves, some more than 15 feet deep and 400 feet long. If we were to peer into the depths of the lakes, down to the bedrock, this is what we would see. Dr. Jeff Dick from Ohio University is looking for clues to how the lakes formed.
The groove that we're sitting in here provides a very interesting tidbit of information as to how the Great Lakes formed. The area that we're in, this groove, was obviously gouged out by some force.
But which force carved these lakes? One of the Earth's most dramatic sculptors is volcanism. Boiling hot magma erupts from deep within the Earth. As it cools and hardens, it can produce incredibly strange geological formations. Did volcanism do it? The rocks at Kelly's Island hold the answer. Tiny coral fossils. When rock melts, the fossil record is usually destroyed. If lava had formed the grooves, these fossils would probably have been erased. The next suspect is water. If water carved the Grand Canyon, why not the Great Lakes? But water has an alibi: fractures in the rock.
If it had been formed by running water, a stream, a river, it's more than likely that that stream or river would have taken advantage of this weakness in the rock and actually followed it, meaning that the fractures would direct where the stream flows. And in this particular case, the grooves are running almost perpendicular to them, suggesting that maybe there's another force at action here.
So if volcanism and running water didn't shape the grooves, What did? There's another suspect. Ice. But how does mere ice carve stone? Where better to find out than Earth's most spectacular frozen landscape, Iceland. This is the Vatnajökull Glacier. It's the largest sheet of ice in Europe. It covers 3,200 square miles. That's more than twice the area of Rhode Island. In places, it's over 3,500 feet thick. Geologist Andy Russell knows it like his backyard.
This glacier, although it may look as if it's sort of sitting there and, fairly passively, the actual ice is always moving forward, even though the edge of the glacier may be stationary.
This time-lapse footage shows the glacier's movement speeded up hundreds of times. Behind the leading edge, the ice moves up to 3 feet per day with a heavy step. A glacier a mile thick exerts about 2,000 pounds of pressure per square inch. That's the weight of 115 cars on 1 square foot of land. For all its bulk, ice isn't as tough as it looks. To cut into solid rock and form the basins of the Great Lakes, ice needs another ingredient. Andy Russell demonstrates.
I shall take a bit of ice, which has a smooth surface, and we'll drag it across this tin foil. Really, there's very little damage to the tin foil. So we'll now move on to the dirty ice.
Dirty ice is embedded with small rocks and stones.
We can see it's got all this grit on it, and we're going to see what it does to the tin foil. The tin foil's been shredded.
That's how a glacier does damage. As it travels, the glacier picks up stones and rocks. The weight of the ice holds them against bedrock. Then the moving mass scours the land like a huge sheet of sandpaper. When the glacier finally melts, it leaves behind a vast depression filled with glacial meltwater. Normally, it's impossible to see glacial erosion in action. The process is hidden beneath a blanket of solid ice. But here in Iceland, the base of the glacier is exposed. It shows Russell just how ice grinds through solid rock and explains how ice could carve the Great Lakes.
We've got layers of ice, which you can see in here, mixed with layers of debris, or it's dirt, here and also here, and obviously this big bit of rock here, this boulder. The boulder tells us several things. All these little scratches crisscrossing, and the fact that this surface here is extremely flat tells me that that boulder's actually been at the glacier bed. It's been held in the ice, and then it's been ground against the bedrock.
This glacier is melting, and as it melts, it drops its load. Iceland is littered with thousands of dropped rocks. It's this action of rock grinding against bedrock that may have gouged out the strange grooves on Kelly's Island. But where's the proof that a giant glacier passed over the Great Lakes area? Here, near the shores of Lake Ontario. Scientists call this an erratic boulder, meaning it doesn't belong here. This giant boulder is made from granite, a type of rock not found within 100 miles of this area. Like the boulders in Iceland, it was trapped inside ice for thousands of years, dragged across the bedrock, and then dropped in its new home. The glacier that moved the boulder must have been enormous. The proof again lies in the rock of Kelly's Island. From the chemical makeup of microscopic fossil shells, scientists can tell the water was once much colder. Tiny clues lead to a vast conclusion. A glacier up to 2 miles thick covered most of Canada and a large part of the US. It was called the Laurentide Ice Sheet. For over 1 million years, the enormous glacier advanced and retreated over the land, back and forth. As it did, it gouged out the 5 enormous lake basins. The ice sheet passed over the Great Lakes. But how long did it take for ice to carve through solid rock and form the basins of the Great Lakes? Geologists think that the Laurentide ice sheet moved across North America for over 1 million years. But how long did it take to gouge out the 5 vast lake basins? In Iceland, the Vatnajökull Glacier erodes bedrock just as the Laurentide once did in the Great Lakes. Andy Russell measures the ground-up rock washed away as sediment.
This equipment measures the cloudiness of the meltwater. The cloudiness of the water gives us a sediment transport rate in the river. And if we average that and scale it up over longer time spans, we can figure out how rapidly the catchment is eroding.
Measure the sediment produced, average it up over time, and this glacier grinds away around 1 foot of solid rock every 100 years. But did the Laurentide erode rock at the same rate? It was, after all, over 1,000 times bigger than the Vatnajökull Glacier. John Menzies has come to Mohawk Bay on the shores of Lake Erie to find out. The answer lies hidden in these cliffs. They look like mud, but they're ancient rock sediment. This was once solid bedrock. It was crushed by the Laurentide ice sheet and deposited here.
Based on the evidence that we're trying to sample here today, we hope that this will illustrate how the Great Lakes basins were formed and developed.
These tiny rock particles hold a secret. Menzies sets the sample in resin and slices it into thin sections. Normally, glacial erosion produces rock grains with jagged edges. These grains are nearly round.
If you look at this particular thin section, you can see this particular piece of rock, and you can see around it the effects of rotation, kind of indicative of the sediment being moved underneath the ice sheet and rolling and rotating beneath the ice. So in other words, the sediment has been tumbled and moved and rotated and sheared time and time again.
But how can a glacier produce both jagged and smooth rock grains? The explanation? Some of the ice inside the Laurentide Glacier moves faster than other areas of ice. The fast-moving ice is called an ice stream. Ice streams are like rivers of supercooled water. Water that's well below freezing, but doesn't solidify. These rivers can flow up to 3,000 feet a year, 10 times faster than the surrounding slow solid ice. Working 10 times faster, they can potentially dig 10 times deeper. More proof that the Laurentide contained fast ice lies beside Lake Ontario. This is an aerial photograph of the shoreline. It shows strange elongated hills. These are lumps of sediment called drumlins. As the glacier retreated, they were left behind. Here's how they formed.
So if we produce a blob of toothpaste, and this we take as the base of the ice, and so as the ice deforms, so does the toothpaste deform, and we produce this nice linear. You can actually see the small lineations, drumlin-like, streamlined forms that are actually being produced simply by moving one interface over another interface.
Just as fast ice leaves a trail of long, thin drumlins, it also tends to carve out long, thin lake basins. If fast ice alone carved the Great Lakes, it could have taken as little as 100,000 years. The ancient ice sheet gouged out millions of tons of rock, ground it into fine sediment, carried it away by meltwater, and flushed it out into the Atlantic Ocean, left behind 5 enormous basins. The deepest, Lake Superior, more than 1,300 feet. The Great Lakes. But when did the enormous Laurentide Glacier melt and the basins fill with life-giving fresh water? Francine McCarthy holds a clue, a 12-foot tube of mud called a sediment core. The sample was taken from the bottom of Willoughby Bog, a swamp between Lakes Erie and Ontario.
This keeps a very good record of what went on when people weren't here to keep the history.
The core is made up of mud, pollen grains, and sediment deposited in the water when the lakes formed.
We remove material for radiocarbon dating, and the dates are about 1,700 years ago here, about 7,500 years ago here, and about 9,000 years ago near the base.
The cores reveal water was present at least 9,000 years ago. But beneath the 9,000-year-old layer is one even older. It's the last layer before hitting bedrock, so it must be the first layer deposited in the water. If McCarthy can date it, she can pinpoint when fresh water arrived and reveal the age of the lakes. But to date the layer, she needs organic material.
You can see the color contrast between the very inorganic and the bog material. This is impossible to date using radiocarbon dating, conventional radiocarbon dating techniques, because you can see that there's very little organic material here.
Just rock and clay, a dead end. But why are the early lakes lifeless? To find out what the early Great Lakes looked like, we need to return to Iceland and the Vatnajökull Glacier. Here at the base of the glacier is a newly born lake. Its basin was carved by ice and filled with meltwater. This is how the Great Lakes looked tens of thousands of years ago. And like the early lakes, this place is dead.
There was virtually no life in these proglacial lakes. It's very cold, it's a very harsh environment, there's very little light, so your whole ecosystem is unable to really get kick-started.
The reason? The water's strange milky color. These lakes are loaded with ground-up bedrock, sediment washed down from the glacier. This sediment blocks out light, and without light, small organisms like algae can't survive. No plants, no food, no life. As the Vatnajökull Glacier continues to melt, more water will flood this lake and dilute the sediment. Eventually, it will settle on the bottom, just as it did over thousands of years ago in the Great Lakes. This is the pale gray layer McCarthy discovered. The mystery remains. Scientists have to find some other way to date the age of the lakes. The answer could lie hidden in one of North America's most spectacular geological formations, Niagara Falls. Niagara is the mightiest waterfall in North America and one of the Great Lakes' most awesome features. On average, 150,000 gallons pour over every minute, enough to fill over 60 Olympic-sized swimming pools. Niagara holds the answer to a prehistoric mystery. When did the ice retreat and the Great Lakes fill with water? John Menzies has come to investigate. It's the first time he's gotten this close to the falls.
It's just utterly incredible. You see the volume of water that's coming over per second. All the water from the central part of North America is flowing right over here as we stand. Fantastic.
It's possible to date the arrival of the water in the lakes because Niagara behaves very strangely. The falls are moving. Every year, they take one step back, 12 full inches toward Lake Erie. The reason for this movement is the rock. The falls are built on 2 layers of rock. At the top of the falls is a hard layer of limestone, known as cap rock. Underneath is a softer layer.
This is a piece of Queenston shale, which is the weaker rock from underneath the cap rock for this area of regional geology. And in fact, it's very, very easily to break, as you can see. Bingo.
The weak shale at the base of the falls is relentlessly pounded at up to 70 miles per hour. The constant hammering erodes the shale below and undermines the cap rock above.
The cap rock gets left like a cantilever effect, and then it simply breaks off, and it breaks off every so often, fairly dramatically. In fact, if we look at the falls, there's a huge rock that's actually fallen off in the last 100 years. In a sense, you can look at Niagara Falls as being, if you like, an ongoing process of destruction. Perpetual destruction, perpetual change.
The destruction means that the falls act like a giant timepiece, an enormous clock that allows geologists to date the age of Niagara and the lakes themselves. Until 100 years ago, the falls eroded 3 to 4 feet a year. As water was diverted for hydroelectric power, the erosion rate has fallen. But the falls are still eroding roughly ½ an inch a month.
Eventually, given time, the hotels, the casinos and so forth are going to be left behind in the track of the falls as the falls retreats to the south and leaves this touristic area in isolation.
If the falls continue to erode at this rate, in about 50,000 years, the falls will reach the base of Lake Erie itself. As the falls retreat, they carve a giant canyon, the Niagara Gorge. 3 miles downstream from Niagara, geologist Francine McCarthy can date the Great Lakes by searching for the fall's birthplace. The secret is hidden not in rocks, but in clamshells.
Well, that's perfect. We can identify that to species. It's definitely the kind of thing we want to radiocarbon date back at the lab.
This species of mollusk lives in Lake Erie. It was carried downriver and over the falls. The surging water wedged the mollusk into cracks at the base, where it died. The falls moved on. The shell remained. By carbon dating shells like this, McCarthy can prove Niagara Falls roared over this exact spot 7,000 years ago.
The water level would have had to have covered this area in order to deposit the little aquatic clams in the crannies where we find them.
Further proof can be seen in the strange rocks scattered around this whole area. These holes were cut into the rock by the constant pounding of water over the falls. But this isn't Niagara's birthplace. The further McCarthy walks from the falls, the further back in time she travels. and the older the shells she discovers. By analyzing shells found all along the gorge, McCarthy reveals the life cycle of the lakes. From Niagara's spectacular location today to their location in 1678, when the first written account was made. Downstream to the Whirlpool Rapids, 5,500 years ago. Through Niagara Glen, where McCarthy's shells reveal their location 7,000 years ago. To Queenston, 10,500 years ago. And finally, 7 miles downriver from the falls, where a natural ridge called the Niagara Escarpment cuts across the land. Scientists discover the oldest shells yet.
The Niagara Falls are 12,600 years old. They've been operating since water started melting from the Laurentide ice sheet.
And if Niagara Falls is 12,600 years old, then the Laurentide Glacier must have retreated at least 12,600 years ago, exposing the 2 lower lakes, Erie and Michigan. The mystery is solved. Like Niagara, the Great Lakes have continued to evolve over the millennia. But some changes happened much more dramatically than anyone imagined. Today, rainfall on Lake Superior takes 204 years to travel through all the other lakes before it reaches the Atlantic Ocean, more than 2,000 miles away. The Great Lakes flow east, and always have, or so geologists thought. Scientists studying fossils in the Gulf of Mexico uncover surprising species. It forces them to reevaluate what they thought about the Great Lakes. Scientists analyzing 14,000-year-old shells discover the water in the Gulf of Mexico must have been less salty than today. But why? Only one source of fresh water was vast enough to dilute the Gulf: the Laurentide Glacier. Fossil records suggest the meltwater drained south along the Mississippi River to the Gulf. But then, nearly 13,000 years ago, some titanic force diverted the flow from south to east. The question is, what force was powerful enough to divert the Great Lakes? 13,000 years ago, some unknown force diverted the flow of meltwater from the Laurentide Glacier. Geologist Alan West searches for answers on the shore of Lake Michigan.
This is a visual line that's actually where our greatest interest lies. The Great Lakes really began right at this line in the sediment.
West finds tiny specks the size of sesame seeds. They're made of carbon. West believes they're all that remains of a vast forest, incinerated at sizzling temperatures. But the most important clue lies inside each grain, a dazzling secret.
These small black dots, they're almost pure carbon, and when we check them with an electron microscope, we find that they contain millions and millions of diamonds.
Each diamond is 1,000 times smaller than a pinhead. They're known as impact diamonds. They form under intense pressure. But what created them? Something big hit this area at great speed. It packed a huge punch. Alan dumps a sample over a magnet. Incredibly, it contains metal.
Definitely magnetic grains in there. You can see them coming out.
The magnetic grains are iridium. Iridium is extremely rare on Earth, but common in rocks from space. West's theory is 12,900 years ago, a massive comet strikes Earth and showers the region with iridium. Wildfires sweep across the area and destroy all vegetation. The shock wave breaks up part of the Laurentide Glacier. Billions of gallons of water are released.
It's well known that when these meltwater outburst floods occurred, they're very, very abrasive. They can change the shape of valleys, they can scour bedrock, so it's entirely possible that they dug the Great Lakes deeper or at least removed sediments that were already there.
Thousands of tons of rock, soil, and debris are flushed south. Like a giant plug, it blocks the Mississippi. The water backs up. Lake Ontario swells and bursts its low eastern bank, and the St. Lawrence Channel opens up.
All the evidence shows that the Gulf of St. Lawrence opened up and water went to the east, but stopped going to the south.
West believes it all happened in just a few months. Since then, the lakes have drained east into the Atlantic Ocean. The new direction allowed small settlements to become the great cities of Montreal and Quebec. Rarely does the course of history change so suddenly and so dramatically. Yet the evidence is circumstantial. If a comet hit, where's the crater? In 1999, on the bottom of Lake Ontario, geologists discovered a crater half a mile wide. It's still undated. West believes it might be a fragment of the comet that diverted the water. No other craters have been found, but West isn't surprised. The comet could have done its damage and simply melted away, because comets are mostly ice.
This is the perfect crime, the ice bullet. Shoot someone with an ice bullet, and you can't tell who did it. Earth got hit by an ice bullet, actually thousands of them, and so the evidence is minimal.
As the last ice age ends, all 5 Great Lake basins are slowly revealed and filled with fresh water. But there's one huge difference between these early lakes and the ones we see today. They aren't linked. To unite them will take a force of nature more powerful than a comet. Today, the Great Lakes are connected via a network of rivers and channels, a 2,000-mile water system. This wasn't always the case. The upper lakes, Superior, Michigan, and Huron, weren't always connected to the 2 lower lakes, Erie and Ontario. Francine McCarthy is trying to find out how they joined.
We've taken some samples all along the shoreline of Lake Ontario and Lake Erie, and we're going to look under a microscope at small seeds and pollen to find out the age of the samples and what kind of environment they were deposited in.
5 miles inland from Lake Erie, McCarthy discovers a tiny clue: wild rice. This is incredibly strange. Wild rice doesn't grow inland.
Wild rice needs to have sort of agitated, well-oxygenated water in order to be happy. The fact that there was a lot of wild rice indicates that the water level in Lake Erie was higher than it is today.
Lake Erie must have been much bigger and more turbulent.
The wild rice date of 4,230 years tells us that water levels rose quickly, instantaneously, in both the Erie and Ontario basins.
But why? McCarthy has a theory. Over 4,200 years ago, Lake Huron swelled and burst its southern bank. A torrent of water pushed south. Lake Erie suddenly expanded, and wild rice took root in its disturbed waters. The St. Clair River opened and the lakes joined.
That's when we begin to see the truly modern conditions. Since 4,200 years ago, there's never been any other way for water to flow out of the upper lakes but through the St. Clair River into Lake Erie, over the falls, and into Lake Ontario.
But why did Huron swell and flood south? The mystery deepened when scientists noticed something strange happening in the Great Lakes. In each lake, the water level in the north is falling, but in the south, it's rising. What mysterious force is behind these strange phenomena? Professor Doug Hunter and divers Luke Clyburn and Kathy Trax are plunging into the lake's past to find evidence of ancient water levels. They start their investigation in Lake Huron's southwest corner, in the harbor town of Lexington. They need evidence to show whether this imbalance in water level is a recent phenomenon or if it's been going on for millennia.
Today, we're going to put divers in the water, and as we dive down, we're looking to see if we can find something that will show this is where the lake levels were some thousands of years ago.
Lake Huron is over 700 feet deep in places. But the area the team are interested in is only 40 feet deep.
Right now, we're about 2.5 miles east of Lexington Harbor. Underneath us, in 40 feet of water, is an area where we suspect there may be some interesting finds that would give us some insight into the Great Lakes history.
This section of the lake bed has never been surveyed. The team scour every inch for evidence of past water levels. They're looking for something out of place, some clue to this strange mystery. "40 minutes into the dive, the team finds several large pieces of wood. From this wood alone, they can't tell if trees once grew here or if it's just debris thrown from a boat. They need evidence like this. A tree trunk. It's still rooted in the lake bed. These stumps have never been seen before. This proves that trees once grew in this exact spot. A true discovery.
There's wood.
Boy, that was a great dive. You could see whole trees falling over, and they just went out into the sand and down.
But once we found the tree stumps, and you could see the roots of the tree stumps running down, it had to be shoreline.
This part of Lake Huron was once a forest of cedar and pine. Today, you have to dive 40 feet to reach the trees. But once you could have walked here and not even gotten your feet wet. When could you have strolled through the trees? These stumps have to be carbon dated, but samples from other locations in the lake have already told their age.
We discovered that the most recent one was 6,400 years before present. The oldest one was about 7,900 years before present. So it's quite a long range, quite a large range of dates.
6,500 years ago, Lake Huron was a fraction of the size it is today. A forest flourished on its southern end. "1,500 years later, water crept south. The southern end was swamped and the forest drowned. The St. Clair River opened, and Lake Huron joined to Lake Erie. The overflow thundered along the Niagara River and tumbled over the falls. And all 5 lakes joined. But what caused this dramatic transformation? And is it still taking place today? Mike Kramer from the Geologic Survey of Canada is investigating a strange anomaly. Why water levels in the Great Lakes are dropping in the north and rising in the south. Kramer works on a remote spit of land next to Lake Ontario. It's not the water level he's monitoring. What looks like a garden shed actually holds state-of-the-art GPS technology.
We're using a GPS receiver to monitor the motion of the structure every 30 seconds. The antenna is bolted down to the floor and runs up through the roof. It's very stable.
In other words, Kramer is studying whether the shed is rising or falling. This GPS receiver picks up signals from satellites orbiting the Earth. The equipment is so sensitive, it can detect movement down to the millimeter. As a result, Kramer can determine the exact elevation of the shed, and thus the land it sits on. His findings are astounding. The Great Lakes region is rising 1 inch per decade in the north and sinking nearly 1 inch per decade in the south. This part of North America is tilting, and the pivot point runs straight through the Great Lakes. The tilt is imperceptible to us, but it affects the lake's water level.
We have a bowl of water representing a lake, this end being the north, this end being the south, and if we can imagine, as the land tilts, the water levels are rising in the south and falling in the north. It appears as though the water level is falling, and actually it's the land that's rising.
The changing land levels are tiny, but over time, all those inches add up. Ultimately, tilting is what drowned a forest. But what force is powerful enough to tilt a major part of the North American continent? Scientists think it's the opposite of the force that compressed it. Earth's surface can actually be squashed if the weight is heavy enough. Few forces are capable of compressing the crust. One is ice. The Laurentide Glacier weighed around 10 million billion tons. Once it reached a certain thickness, the glacier depressed the crust 1 foot for every 3 feet of ice. It left a dent up to a half a mile deep.
About 20,000 years ago, the ice had covered most of Canada, and the great weight of that ice had depressed the crust substantially. And as the ice retreated and melted, the land underneath it then began to rebound.
Rebound began as the ice melted tens of thousands of years ago, and continues to this day, about 1/10 of an inch per year. The ice sheet was much thicker in the north than it was in the south. At its thickest, it compressed the Earth the most. So when the weight was removed, the Earth rebounded more in the north. This imbalance causes much of North America to tilt. Combined with a warming climate and less rainfall, rebound is changing the outline of the Great Lakes. If water levels continue to drop in the north, vital transport routes will shrink. Industry, hydroelectric power stations, and millions of people could be affected. Eventually, the crust will rebound to roughly the position it was before the Laurentide Glacier advanced over it, and the water will find its level. But until it does, the future of the Great Lakes will be as dynamic as their past.
In the empty blackness of space, surrounded by hostile planets and freezing vacuum, planet Earth is an oasis of life. And all because of our protective cocoon of gas. This blanket of air shapes everything we see on Earth. It protects, insulates, and sustains us. It carries water around the globe and shields us from cosmic impacts and killer radiation. It's time to uncover the invisible wonder that is our atmosphere. Down here on the Earth, we rarely give much thought to our atmosphere. Because we can't see, smell, taste, or hear it, we take it for granted. But our air is all that stands between us and the vacuum of space.
We've got this canopy that provides us a lot more than just an atmosphere to breathe in. It definitely shields us.
The atmosphere is divided into 5 distinctive layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer is less dense than the one below, stretching miles above our heads.
How far out it goes is depending on which scientist you talk to. Some say it ends at 300 miles, some say it extends out to Mars.
We live in the layer closest to the ground. Here in the troposphere, the air is thickest and the pressure greatest. Our bodies are perfectly matched to these conditions.
Our chemistry, our very nature, our metabolism is completely shaped by the atmosphere.
To appreciate our atmosphere, we'll rise through its layers, traveling from the planet's surface, miles up above the mountains and the clouds, to the very edge of space. August 16th, 1960. One man is preparing for a record-breaking journey into the mysterious skies above. To a lethal world above 99% of the Earth's air, where an unprotected human would die in seconds. Where the temperatures plunge to 67 below, and the air pressure is 1/100th of that at the surface. Colonel Joseph Kittinger will travel almost 20 miles high. And then he will jump. This is a key military mission, one of the first steps in the space race. Kittinger will be testing the human body's resistance to high altitude, low pressure, and rapid free fall. He will be trialing new technology he hopes will protect him.
It had never been done before, but we were not there to set a record. We were there to gather information that we needed for our space program and for our high-flying aviators.
Ground crew prepares his vehicle, a helium balloon, and a rudimentary open-sided gondola.
Just an open gondola. It was designed just to carry me up there. It was a space platform, an elevator, I called it.
At 5:30, Kittinger's preparations are over. He boards the gondola.
My crew chief said, "Are you ready?" I said, "I'm ready, let's go." It was a very smooth takeoff, and I started ascending. Up, up, up.
30 minutes after takeoff, Kittinger reaches 29,000 feet, the middle of the troposphere. At this altitude, the air is so thin that each breath contains only 1/3 of the oxygen found at sea level. Kittinger breathes from gas bottles connected to his sealed helmet. He's still barely 1/3 of the way to the jump point. There are another 14 miles to go, and the air pressure is dropping rapidly.
So at about 40,000 feet, suddenly the pressure suit starts inflating, and that's when you start checking it to make certain that it's working properly.
But there is a crucial fault in the suit. The glove covering his right hand is not sealed.
I had an option to tell the ground that I had the problem, and I knew that if I did, they'd probably make me abort the flight. And I was concerned that if we had to abort that flight, that we would have been turned down to try to do it again. So I didn't tell them.
Kittinger prays that this is an isolated fault, and continues to climb at 1,000 feet per minute. After 89 minutes, he approaches his target altitude. The balloon's climb slows and then stalls. Kittinger is in the mid-stratosphere, a record 102,800 feet high. And it is now time to make the long, swift journey down.
When it came time for me to jump, I was ready to jump because I was heading back toward a more friendly environment, a friendly planet that we're used to. I had made this jump 1,000 times in my mind. I'd gone through every step 1,000 times. Well, just before I jumped, I said a silent prayer. I reached over and hit a button that started the cameras going. And then I just did a little hop off the step of the gondola. You can't tell that you're going fast, you can't tell anything. And I looked up at the balloon, and the balloon was firing into space. And I said, gosh, that's amazing. And then I realized it was me that was going down at a fantastic rate, and the balloon was standing still.
He falls for 16 miles. The thin air offers almost no resistance. He reaches 614 miles an hour, approaching the speed of sound. After a record-breaking 4 minutes and 36 seconds of freefall, Kittinger opens the main parachute. He drifts down to the desert floor and lands.
We were just elated because we had accomplished what we set out to do. There was a lot of people who said we couldn't do it, and we proved that we could do it.
The mission has been a stunning success. Kittinger's skydiving record stands to this day. He takes his first deep breath of air with a newfound appreciation for our atmosphere.
It was a relief to be back on the planet Earth that we love so much, a planet that has an atmosphere that we can live daily.
Kittinger forged a dizzying path through the atmosphere. Our journey begins just a few feet off the ground with the air we breathe. We take for granted Earth's blend of gases, the perfect mix for heat and energy. And astronomer David Grinspoon believes we'd be hard-pressed to find its equal anywhere.
The more we learn about planets, the more we learn that they're all individuals. They're like people in that sense. So as far as what we know now, Earth's atmosphere is completely unique.
In the past century, telescopes and space probes have uncovered the extreme atmospheres of our neighboring planets. A journey across our solar system reveals exactly how unusual Earth is. Clouds of near-frozen gas flow over the icy surfaces of Uranus and Neptune, while the sun has blasted away the atmospheres of Mars and Mercury.
To me, it seems as though Mercury doesn't have an atmosphere at all. In fact, if you were on the surface of Mercury, it would look to you as if you were out in outer space.
In contrast, Jupiter and Saturn are all atmosphere.
Unlike Earth, Jupiter doesn't really have a solid surface that you could stand on and then have your head up in the atmosphere looking at the clouds. It's just a giant, giant gas ball.
Only one other planet shares the Earth's thick atmosphere and rocky surface: our near neighbor, Venus. But even here, there are striking differences. Dr. David Crisp has spent 20 years studying Venus's acrid air.
Imagine you're at the surface of the planet Venus. You're at pressures that are high enough to crush a nuclear submarine. The pressures there are about 90 times the pressure of the Earth's surface.
This pressure is combined with extreme heat, 900 degrees Fahrenheit, hot enough to melt lead. Clouds drift over the baked surface, but they are not water vapor. Venus's clouds are made of concentrated sulfuric acid. Venus is a stark example of how extreme an atmosphere can be. But the real mystery isn't why Venus is so hostile, but why Earth hasn't followed the same path.
As planets go, Earth and Venus are essentially twins. They're almost exactly the same size. They're also very close together in the solar system. In spite of that, their environments evolved in dramatically different ways.
To discover why these twin planets followed separate paths, and to explore what gave us our precious atmosphere, we have to travel back 4.5 billion years, to the birth of the solar system itself. The birth of the solar system created Earth's earliest atmosphere. Huge quantities of material orbiting the sun fused together into protoplanets. Jupiter and Saturn formed into gassy spheres. But on Earth, most of the material condensed into a molten core. The remaining gases bubbled forth from the liquid rock, forming the first atmosphere. Our planet's gravity stopped these gases from drifting off into space. But Earth now had to face the ravages of the solar wind, a stream of charged particles thrown out by the sun. This same wind had a catastrophic effect on Mars. It has stripped the air from the planet's surface, blasting it deep into space. The red planet's atmosphere is now only 1/100th as thick as Earth's. Our planet was spared this fate. The magnetic field generated by the Earth's core blocked the solar wind, preventing it from blasting away the fragile air. But the Earth's atmosphere was still very different from the one we breathe today. It contained high levels of carbon dioxide, a gas with a key ability to absorb and hold on to heat. Carbon dioxide still makes up 95% of Venus's atmosphere. It superheated our twin planet to the point where its water boiled away into space. And yet, this didn't happen on Earth. David Crisp believes that was down to a chance event.
If Earth kept all of its initial atmosphere, it probably would have turned out a lot more like Venus. But that didn't happen. We were the victims of a very lucky accident.
Earth's big break came 4.5 billion years ago. Back then, the solar system wasn't limited to the 8 planets it has today. Instead, a swarm of protoplanets, or planetesimals, orbited the sun like bees around a honeypot. One Mars-sized body was heading straight for Earth. In a colossal cosmic collision, it slammed into our planet, creating our moon, and according to Crisp, removing the atmosphere that still blights Venus. This ancient event was the defining moment for our atmosphere. With the original deadly gas mix blasted away, our planet's air could slowly evolve into what it is today.
We were left with this atmosphere made of molten rock and vaporous rock. It took millions of years for that atmosphere to fall out and to be replaced by an atmosphere made up of nitrogen and carbon dioxide and water vapor.
These new gases came from above and below. Volcanic eruptions spewed out fresh stalks of nitrogen and carbon dioxide from within the planet's molten core. While the vital element of water may have been delivered by icy comets, each impact bringing a new supply of frozen liquid. But the air still lacked one of its key ingredients.
One of the things that was missing is free oxygen, molecular oxygen, O2, the stuff we breathe.
Dr. Janet Seifert of Rice University in Texas searches for the event that produced the atmosphere's final element.
We know from the rock record that for the first half of Earth's life, there was no oxygen in the atmosphere whatsoever. There were greenhouse gases like methane and CO2, but there was no oxygen.
But the rock record shows a sudden change, dated to around 2.5 billion years ago. Evidence of the first oxygen in the atmosphere. The gas was released by a humble microscopic living organism called cyanobacteria.
What turns out is cyanobacteria are the only things that can actually produce oxygen. So we know that at some point cyanobacteria colonized enough of the planet in order to produce enough oxygen that it became resident in the atmosphere.
As the microbes multiplied and spread, the gas built up in the air, transforming the planet in a process known as the Great Oxidation Event.
Oxygen is very powerful. The world gets turned upside down. Everything has to begin to adapt to now a completely new atmosphere where oxygen is dominating.
First, the oxygen reacted with the oceans, causing iron within them to form rusty deposits on the sea floor. Then its effects reached dry land. It reacted with soil and rock, giving them a reddish, rusty tinge. And once these minerals had absorbed their fill of oxygen, the gas began to gather in the atmosphere, with dramatic consequences for life.
Complex animals could have much higher metabolisms because of the sheer potential that oxygen provided for them, and a whole different kind of evolution was able to take place.
Powered by oxygen, life evolved from single-celled organisms to complex animals. And plants also began releasing oxygen, thanks to an ancient adoption of photosynthesis.
A very ancestral, primitive plant cell either engulfed or tried to digest or surrounded a cyanobacterium. And instead of digesting it, it actually became an organ within the plant. So every bit of the oxygen, even if it's coming from a plant that you see in your yard, is coming from an ancestor of a cyanobacteria resident inside the plant.
With the rise of oxygen, the air's unique blend of gases was complete. This air we breathe has changed planet Earth, molding its terrain and habitats. And as we continue our upward journey, we run into another vital substance, water. The turbulent movement of our atmosphere carries water vapor around the globe. Powerful winds and violent storms smash our buildings and drown our fields. But without them, the land would be bone dry. Our atmosphere is in constant motion. The moving air that causes our weather circulates between the ground and 50,000 feet. It is the sun that drives this movement. When solar energy reaches Earth, it heats the surface and atmosphere, but it does so unevenly. This temperature difference causes the air to move. Hot air near the equator expands and rises. Cold air at the poles becomes denser and sinks. NOAA's Marty Ralph can track its movement over the globe on the revolutionary Science on a Sphere simulator.
What we're seeing here is a portrayal of the Earth's surface temperature, and red and warm colors are warm temperatures like we see in the tropics here. Up in the poles, you see the blues and the greens. Those are the colder surface temperatures. So we can watch this and actually see the warm air moving northward, the cold air moving southward, and we can see the changes in the seasons.
If the atmosphere didn't move, the poles would be 45 degrees cooler and the equator 25 degrees warmer. The great deserts of the Sahara, Atacama, and Mojave would expand dramatically. Northerly cities like London or Boston would be locked in an icy winter. It is only the atmosphere's circulation that prevents this. It regulates the temperature, moving the air to create the weather that covers our globe. The planet's rotation twists the air as it flows, helping form the hurricanes that lash the coasts. As moist air wells upwards, clouds become electrically charged and send lightning bolts crashing down to Earth, superheating the air to 18,000 degrees. And as the air cools, water vapor condenses into clouds and rain. This water evaporates from the world's oceans. At any moment, 0.1% of the world's water is being carried in the air. But that tiny percentage adds up to almost 3,000 cubic miles of liquid. If the air didn't carry water, the land would be bone dry.
Storms do a really important job for the atmosphere. They help reduce the difference in temperature between the poles and the equators. And in the process, they actually create the rain and snow that we depend on.
One of the most powerful weather systems is a newly discovered set of water channels running through the air. Ralph's current research focuses on these mysterious rivers in the sky.
One of the phenomena that really influences where the water is available for us are these regions where water vapor transport is focused. We've come to recognize that phenomena as an atmospheric river.
Atmospheric rivers are narrow channels of hurricane-force winds that can stretch for thousands of miles. A single river can carry 3 times as much water as the entire Mississippi. They provide almost half the annual rainfall for parts of the American Pacific coast, but when they remain over one area for a day or more, they can produce violent flooding.
Heavy winds, lots of water vapor, a storm track that's not moving fast, adds up to a big flood event.
The rivers were only recently discovered because they form over the world's oceans. We still don't have enough data to forecast their floods.
An example of the challenges we face in weather prediction is that while this model can actually produce an atmospheric river, like we're seeing right here, a week ago today we looked at the forecast for today, and it said there should be a strong atmospheric river creating heavy rain in Northern California. Well, instead, it's hitting Canada. That's a huge difference.
To fill the gap in data, Ralph explores the rivers on research flights. The rivers form in front of banks of cold air. They create channels of wind that carry huge quantities of water vapor from the ocean to the coast at up to 100 miles an hour.
These are like conveyor belts for water vapor. They're very narrow, and yet they do 90% of the water vapor transport for the global atmosphere at those latitudes.
When the airflow hits a mountain, it rises up, shedding its water as rain and snow. Ralph has tracked how the rivers move with the changing seasons. But to fully forecast the floods, he needs a lot more atmospheric data. He believes robotic drone aircraft, developed for the military, could continually measure the air over the oceans, charting its temperature, winds, and humidity. And the flights could also track how the rivers are changing.
We're starting to see evidence that the more intense atmospheric rivers might become more frequent in certain parts of the world, and that will contribute to increasing the frequency of flooding.
The changes Ralph has identified are part of a wholesale shift in our climate and atmosphere. Deserts are expanding, while rainforests are drying out, all due to a change in the chemical makeup of the air. This blend has always been in flux. We alter the proportions with each breath we take. But our factories and homes, planes and cars, amplify the process. For over 2 centuries, we have been dramatically increasing the amount of warming carbon dioxide in the atmosphere. So far, the planet's natural air filters have pulled nearly 55% of it out of the air.
The North Atlantic has absorbed a tremendous amount of carbon dioxide, but at the moment it's almost completely saturated by carbon dioxide, so it's not absorbing very much more. It's almost like a bottle of some kind of soda pop. If you warm it up a little bit, it'll actually fizz and release CO2.
As these natural safety valves close, we will face an even more dramatic rise in temperatures. The global average could be up 7 degrees Fahrenheit by the end of the century, wreaking havoc with weather patterns and habitats. We can prevent climate change by preserving the air's delicate blend of gases, the unique mix that sets Earth apart. And our planet is also marked by how this blend sits above the surface in a distinct layered structure. As we rise above the clouds and winds of lower altitudes, we enter a completely new zone. A world of extreme temperatures and ever-thinning air. Air that would kill us in seconds, but which shields us from deadly radiation. We live in a tiny sliver of Earth's atmosphere called the troposphere. Winds and clouds, rain and snow dominate this turbulent zone, but above it lie miles of freezing dry air. The conditions there would kill a human in seconds, but we desperately need the high atmosphere's weight and protection. Engineer John Powell's balloon team has spent 27 years exploring its layers, pushing further and further into this remote, dangerous world.
Sometimes we just run into a phenomenon that we have no idea what that was. We just have this moment of data in it that we need to go back and explore. But it really is like a completely alien, foreign world up there.
The team has made over 90 launches. Each one edges them closer to their ultimate goal of reaching space.
You can use balloons not just to go to the edge of space like we do now, but go all the way over the line and actually use balloons or airships to go all the way into space. Space travel without the rocket.
Officially, the atmosphere ends and space begins 62 miles up. This sounds high, but on a tabletop globe, that would only be as thick as the coat of varnish. And in reality, the air extends out much farther. The atmosphere's lowest layer, the troposphere we live in, ends 40,000 feet up, the cruising altitude of airliners. Above are another 4 distinct layers.
They're all separated by their temperature. It gets colder and colder and colder, then it warms up to a nice toasty 0, and then it starts to get colder again. So whenever the temperature changes directions, you know you've made it into another layer.
First comes the stratosphere, a stable layer without strong winds. Then temperatures in the mesosphere plunge to minus 150 degrees Fahrenheit. Above that is the thermosphere, where solar radiation can push the thermometer back up to 4,500 degrees. And finally, there is the exosphere, an endless zone where air molecules slowly thin out into the pure vacuum of space.
Now, the exosphere is really high. They actually detected particles of the Earth's atmosphere on the far side of the moon during the Apollo program.
As Powell's balloons rise towards space, they leave the world we know far behind. The air thins, and they begin to lose the protective weight of the miles of air above them.
The pressure is dropping. When you finally get to the stratosphere, to the altitude we like to work at, it's only 1/100th that of it is on the ground. It is a whole different world than down here.
The weight of the miles of air above us creates air pressure. We often think of air as weightless, but all those gas molecules add up. Grand Central Station's main concourse contains over 200 tons of air. As gravity pulls the air down, it compresses the layers below, making them denser. This dense air is what we are used to dealing with on the ground. Just a pint of it contains more than 8.5 billion trillion gas molecules. But higher up, around the balloon, there is less atmosphere pressing down from above. The air up here is thinner.
It's like being under 1,000 blankets, and each blanket is a layer of the atmosphere. And we're being pushed under all of these blankets. Now, as you go higher, you're going up through the blankets, so it's pushing on you less, until you're at the top, then above most of the blankets where you don't feel it at all.
That thin air seems alien to us because our bodies and technology are so perfectly adapted to thicker air. We even need it to hear. The gas carries sound through air as pulsing waves of pressure.
Sound is just a wave, like a water wave in a pond. But if you take away the water, there's nothing for the wave to go across. And as the atmosphere gets thinner and thinner, it supports that wave less and less and less.
Finally, in the vacuum of space, there is nothing to carry the wave, and even the largest explosion is silent. School science experiments on board the airship studied the dramatic pressure change.
And we call it a PONGSAT, for ping pong ball satellite. And it's real simple. The first thing they do is they have to cut the ping pong ball in half. Then your experiment goes inside. And the simplest and my favorite is where you take like a little mini marshmallow and they just drop it in the ping pong ball. This is satellite construction at its best. And then we take them to the edge of space.
In the thin air of the stratosphere, the marshmallow is no longer held together by high air pressure. Air bubbles inside it expand, causing the spongy candy to bloat outwards and burst open the PONGSAT. Just as the thin air is dangerous for marshmallows, it can also affect flesh and blood. Contrary to popular belief, your blood won't boil. It's held in by your blood vessels. But any exposed flesh will swell out like the marshmallow. And at around 26,000 feet, the air is too thin to breathe. There just aren't enough molecules in every lungful of air. And starved of oxygen, your brain will begin to shut down.
You know, the extreme cold would get you, but the lack of pressure would get you first.
As the balloons rise higher still, they face attack by an invisible bombardment: radiation. Every day the sun radiates a titanic amount of energy, some of it in the form of high-energy ultraviolet rays. These rays pack a powerful punch, and in the high atmosphere, they attack the structure of Powell's balloons.
The UV literally damages the material, and you start getting microscopic cracks in the material, which makes it brittle. You know, eventually it just fails, and the balloon pops.
The rays are potential killers, both for balloon and human. They bombard our cells and DNA, triggering cancers. But around 7 miles up, a layer in our atmosphere shields us from 99% of these rays. It is made up of ozone, a rare molecule of 3 bonded oxygen atoms. This can absorb and block high-energy UV rays.
The ozone layer, it's not like this saran-wrapped thick layer, a boundary that you pass through. It's actually miles and miles thick, so it's a slow diminishment.
Man-made chemicals used in refrigerators and aerosols have been eating away at this delicate protective layer. Every winter, holes in the shield appear over the poles. The harmful chemicals are now banned, and the layer is beginning to recover. And above it, the fragile air of the mesosphere is shielding us from another deadly barrage from space. In East Texas, Jeff Notkin and Steve Arnold are searching for the remains of cosmic missiles that have been shattered by our atmosphere. Fragments rarer than diamonds and worth their weight in gold. Meteorites. These two professional hunters seek out space rocks buried in the fields and prairies.
This search for meteorites allows me the chance to touch a little bit of what's from out there, bits of the cosmos that have found their way to us.
The hunt has taken Steve and Jeff from Siberia clear down to Chile, and some of their finds have been spectacular.
The largest meteorite I found was 1,430 pounds. It was a large stony iron meteorite from up in Kansas. We didn't realize it was that big of a deal. The media kind of picked it up and ran with it.
He's very modest. It's not only Steve's greatest find, it's one of the greatest finds ever made in meteorites.
The massive space rock has been valued at up to a cool $1 million. But this is a rare find because most meteorites simply don't survive a brush with Earth's atmosphere.
Most of them don't make it to the surface. The atmosphere is our friend in the sense that it protects us from these rocks from space, but for meteorite hunters it's also not our greatest ally because it burns up a lot of what we're looking for.
Steve and Jeff search for remaining fragments using a custom-built metal detector rig.
Meteorites will have iron in them, and it's ferrous, and so not only will a magnet attract to it, but also a metal detector will be able to pick it up.
Every year, over 18,000 meteorites lock onto a collision course with Earth.
When meteorites encounter our atmosphere, they're traveling at the speed that they acquired while moving through the vacuum of space. And typically, they're traveling at many thousands of miles per hour.
As they head down to Earth, they cut through the outer reaches of our atmosphere. But once the meteorites enter the mesosphere, the air starts pushing back.
We can't see the air around us, and we can only feel it on really windy days like this. But a meteorite encountering our atmosphere definitely feels the air. And that is because it's traveling so quickly. When it encounters our atmosphere, the air in front of the meteorite cannot get out of the way in time. It's almost like the meteorite hitting a solid wall, like a block of concrete.
As the air in front of the meteor compresses, it also heats up to more than 30,000 degrees Fahrenheit. Eventually, it bursts into flame, lighting up the sky. When you see a falling meteorite or shooting star, it's actually the protective shield of air that you see burning, not the meteorite itself. But the friction and heat wears away at the space rock. The hot air actually melts the metal surface. And often the collision with the atmosphere can have a shattering effect, splitting the meteorites along fissures.
This is an actual meteorite, and if this were to encounter the atmosphere at high speed in its current condition, and that's the result.
Only fragments of the original asteroid survive the fall to Earth. Their speed has dropped from 17,000 to 300 miles an hour. Rocks as big as station wagons have shrunk to the size of golf balls. They impact on the surface, forming holes a few inches deep. The chances of finding one are remote.
There we go.
I'll get the shovel.
Right about there, Maestro.
It looks promising, but this time the guys are out of luck.
So yeah, we found a plow, and basically a lot of different types of trash can be in these fields, and so anything that's ferrous, our detector's going to pick up. Meteor wrongs, as we call it, as opposed to a meteorite.
On average, they uncover 75 meteor wrongs for every meteor right.
This is a genuine iron meteorite. This is believed to have once been part of the core of a long dead planet or asteroid. And this was found right here in this strewn field. These remarkable little shapes indentations on the surface are called thumbprints, or scientifically regmaglyphs, and that's a feature that's unique to meteorites. And these little markings are caused by the surface actually melting as it flew through the atmosphere. We don't find regmaglyphs on Earth rocks.
The air is constantly at work, making meteorites rare and valuable.
The chances of meteorites surviving their journey through the atmosphere and being found are minuscule. If it wasn't for our atmosphere, we would have little particles raining down on us all the time, and some of them not so little.
The mesosphere's barrier of thin air is the final gift from our atmosphere, adding to the oxygen we breathe, water we drink, and pressure we feel. But as we cross into the layers above, we leave life far behind. John Powell's airships have only reached the upper stratosphere. Kittinger's jump point is below that, in the middle of the stratosphere. The only people who travel through the superheated thermosphere and distant exosphere are astronauts, heading for space. One day, these manned space missions may reach out even further, to distant planets with alien atmospheres. Atmospheres that may support their own life forms. Elsewhere in our universe, on distant planets, alien air may support extraterrestrial life. Joel Hagen has spent 20 years imagining how those atmospheres could have affected their inhabitants.
That's where some of the real creative joy comes from, is trying to think about everything that has happened here and then take yourself one notch beyond it and imagine, what haven't I seen yet? And then try to visualize that.
One of the possibilities that intrigues Hagen is life on a gas giant planet.
This is an environment so completely alien to what we're used to. Even a planet like Jupiter, for instance, has no solid surface, just a gradual transition of densities of gases. And I think we might imagine creatures in an atmosphere like that that sort of relied on buoyancy, perhaps being able to generate hydrogen, for example, somehow within their bodies.
These creatures would be like hydrogen-filled blimps, lighter than the air, able to float amongst the gas clouds.
The concept that I have here is to have perhaps colonies of microbes in these sort of tentacle-like structures here. And these microbes generate the hydrogen, which in turn sort of inflates the gas bag here. A creature like this then could sort of float freely at certain levels in the atmosphere.
On other planets, with denser atmospheres, larger, more complex creatures could take to the skies. The thicker air would support them aloft, allowing bulky reptiles to glide and fly.
This creature probably wouldn't be able to fly very well on our planet, but even on a planet like Titan, for instance, it has a surface gravity only about 15% of Earth's, but an atmospheric density at ground level about 1.5 times. Even a person with wings strapped to their arms could fly in an atmosphere like this, so we could have creatures like this.
Hagen bases his ideas on known planets and the evolutionary history of Earth. But it's all pure speculation, until we find life in alien atmospheres.
I would be pretty thrilled just to find microbes under rocks on Mars, for instance. They don't have to walk up and shake hands with me to get my blood up. I would be pretty happy just to know that life has happened twice.
At present, we are alone. Life may have happened just this once. And if it did, then it's only because of our planet's unique atmosphere. As we have soared for miles above the ground, we have journeyed through this ocean of air. The air which shields us, supports us, and sustains us with every breath.
Diamonds. 4 billion years old, and they still dazzle us. But these rocks aren't just for show anymore. Hidden inside are powers that could change your life.
The future of diamond is very exciting and opens up what many of us have been calling the new diamond age.
To reach that shining future, Scientists have to outdo nature and build a better diamond.
The new synthetic diamonds, that's a technology that's going to take us places we've never been before.
It's a dazzling challenge. Can science do the unnatural and make a super diamond? Diamonds are like no other substance. They're 4 times harder than any mineral on the planet. They resist corrosion. The best are completely transparent. And they conduct heat. Some can conduct electricity.
What you have is a material such as diamond that has a fantastic range of unique properties, and it's the combination of these unique properties that makes diamonds special.
If science can harness the powers of these stones, it could revolutionize our lives. From the microchips in our phones to the machines that explore space.
They'd be super durable, they'd last forever. They'd be resistant to heat and cold and the other kinds of extremes.
It's said diamonds are forever, but they aren't. Most contain natural flaws. Flaws that can't withstand extreme heat and pressure. To transform technology, science must do something unnatural. Create the ultimate diamond in the lab.
Nature is the guideline, and the question is, can we improve upon it? The race now is to produce a super diamond.
A super diamond would have all the properties of a natural diamond, but could be manufactured in any shape or size. Most of all, they would mimic the properties of the rarest gems, like this one. The Hope Diamond, perhaps the world's most perfect natural diamond. It's kept behind bomb-proof glass in the Smithsonian Institution in Washington, D.C. At 45.5 carats, this gem is over 100 times bigger than the average diamond ring. It's one of the largest and most valuable diamonds ever discovered, worth around $250 million. But that's not all. This gem has some unusual properties that highlight what makes diamonds so special. Jeffrey Post, the curator of the National Gem Collection, is researching this stone. In the lab, he demonstrates a phenomenon that sets the Hope Diamond apart from most others.
We can take an ultraviolet light and we can expose the Hope Diamond to the ultraviolet light, and we'll leave it on for about 10 or 15 seconds. Also notice that one of the white diamonds on the outside fluoresces very bright blue. And so now we're going to turn the room lights off, and I'll turn off the ultraviolet light, and we can see the intense orange glow, the property called phosphorescence.
For years, this glow was attributed to a curse cast over the diamond when it was stolen from an Indian temple centuries ago. But Post isn't superstitious.
So here you've got supposedly a cursed diamond that glows this blood red color. Well, you know, that's a great story in itself. But then the scientist in many of us says, well, why does it do that?
Post and his team investigate using a spectrometer, an instrument that analyzes wavelengths of light. The spectrometer shows that the Hope's distinct hue comes from 2 colors, aqua and red. The team can now identify 2 chemical elements in the diamond, boron and nitrogen.
Suddenly, now I understand what is going on when this diamond is phosphorescent.
Boron makes the stone blue. When combined with nitrogen, the stone shines red. Chemicals, not a curse, make the hope glow. It's not the red glow that excites scientists, but the element that makes the hope blue, boron. Boron does more than color diamonds. It also allows them to conduct electricity.
Blue diamonds, because of the boron present in them, are in fact semiconductors of electricity, which makes them very different than other diamonds that are pure carbon.
Pure white diamonds are electrical insulators. Try to pass a current through them, and nothing happens. But blue boron-rich diamonds, like the Hope, are electrical conductors. The extra atoms of boron interact with the existing diamond atoms, letting an electrical current pass through. But all diamonds, not just blue diamonds, have another useful property. They transfer heat better than any material known. If science could make synthetic diamonds that both conduct electricity and transfer heat, they could revolutionize a critical component of daily life, the semiconductor. Semiconductors are the vital component in nearly every electronic device. In transmitting electricity to the precision control of microchip technology. For the past 50 years, these devices have been made almost exclusively from silicon. But silicon has a major drawback. The more electricity it carries, the hotter it gets. The result? Most silicon chips require complex cooling technology. If they exceed about 300 degrees Fahrenheit, they'll shut down.
One of the huge hurdles that are facing manufacturers is that they have to be able to remove the heat away from these electronic systems. You know, think of your own laptop at home as you're operating it. It gets hot. And so this becomes a big problem. Right now they're using metals mostly to do that. But diamonds, in fact, are much better conductors of heat than metals are.
With the discovery that blue diamonds transfer heat and conduct electricity, scientists can imagine the unimaginable. A world beyond silicon. A world where everything from your cell phone to a spacecraft runs on diamonds. Diamonds can carry 30 times more power than silicon and operate 3 times faster. And they're so efficient at transferring heat, they could run a computer at speeds that would melt a silicon chip. They also resist temperatures over 1,800 degrees Fahrenheit.
To be able to coat electronics with diamond or use pieces of diamond as the heat sinks would certainly offer a whole new direction for the manufacture of even smaller, more powerful electronic devices.
Despite their eye-catching sparkle, diamond's real potential has been overlooked for centuries. The possibilities for technology are almost endless. But there's one problem. Diamonds are rare and expensive. Natural semiconducting diamonds like the Hope are thousands of times more rare. And they don't come in the right shape or size for industrial use. So scientists are trying to create a synthetic super diamond with all the powers of a natural blue diamond, but in a size and shape of our design. To succeed in creating a super diamond, scientists must first discover how nature made hers. And for the answer, they look to the stars. For scientists to create a synthetic superdiamond, they must first get back to basics and investigate the ingredients of a natural diamond. For all their rarity, diamonds are made from one of the most familiar elements on Earth, carbon. Carbon is so fundamental, it forms the basis of everything around us. Even we are 18% carbon. It's so common, it's estimated that our planet contains over 100 billion tons of it. But carbon doesn't originate on Earth. It comes from long ago and far away. A star on the brink of death. A red giant. Astrophysicist Neil deGrasse Tyson studies carbon's dramatic formation.
Well, the universe is born without any carbon. Our sort of birth ingredients are hydrogen and helium and just trace amounts of lithium. So carbon comes later. Carbon is forged in the cores of stars.
This red giant star once looked like our sun. But as it ages, it grows over 1,000 times bigger. Instead of glowing white hot, it glows red as it reaches the end of its life. It's running out of fuel. Its core is now composed almost completely of helium. In its death throes, a nuclear reaction in the core breaks down helium and fuses it together in a new configuration, carbon. Dying red giants are the universe's carbon factories. Eventually, the star explodes in a white-hot flash, so strong that billions of tons of carbon are flung out into the farthest reaches of space.
What happens is the star collapses, and the entire core, in response to this collapse, rebounds and explodes. A titanic explosion we call a supernova. And its guts are scattered everywhere. And it's a spectacle. It's so much of a spectacle that you can see these stars explode halfway across the universe.
In time, the vast cloud of debris from the explosion is pulled into orbit around a new star. As this debris spins, it clumps together. Over millions of years, these clumps grow, and planets begin to form. This is how our solar system and our planet itself was born. And it's why Earth holds the raw ingredient for diamonds, buried deep in huge quantities: carbon. For scientists hoping to create a superdiamond, a problem. The form carbon usually takes is weak. Carbon in its most familiar form is graphite. Great for pencils, but far too soft for high-tech products. Bob Hazen, research scientist at Washington, D.C.'s Carnegie Institution, is an expert on carbon and diamond formation.
You know, it's amazing. Diamond and graphite are made out of the same element, carbon, but they're so vastly different. Graphite has these planes of weakness, and you can see how every one of these black dots, the carbon atoms, are connected to 3 other carbon atoms in a triangle. But in diamond, every carbon atom is now connected to 4 adjacent, and this trellis, this network, this lattice. So diamond is strong in every direction. That's the difference.
For scientists hoping to create a superdiamond, making it hard will be tough. They have to recreate a diamond's lattice-like structure. To do that, they have to figure out how nature turns basic carbon into a dazzling diamond. Scientists are on a quest to figure out how to make a super diamond. Their search begins here, South Africa, diamond capital of the world. Diamonds were discovered in these rocks in the 19th century. Hundreds of thousands have been mined here, but only recently did scientists learn how they actually formed. Professor Steve Haggerty is an expert on how diamonds are created.
Diamonds were a real mystery in terms of their origin. They were found in clusters. So you found one diamond, and by golly, there would be others to be found as well. So that led to the notion that the process in which the diamonds were brought to the surface was possibly deep.
Diamonds form deep within the Earth in an area called the mantle, the layer between the Earth's crust and its superheated core. Down here, intense pressure changes the molecular structure of carbon by crushing its atoms together and forcing them into a new lattice-like structure. Under extreme pressure and temperatures, carbon becomes diamonds.
The temperatures have to reach about 1500 degrees centigrade and the pressures about 50 kilobars.
That's 2,700 degrees Fahrenheit and the weight of over 4,000 grown men standing on your foot. The journey from a dying star to a diamond mine is almost complete. 100 miles still remain between their source in the mantle and the Earth's surface. Luckily, they're fast-tracked to the surface by a substance called kimberlite.
Kimberlite is the rock, it's the host rock to diamonds. Even though the diamonds do not form in the rock, it's the transporter.
Kimberlite is a volcanic rock that forms deep within the Earth. As it moves to the surface, it creates a carrot-shaped pipe filled with molten rock, mantle fragments, and diamonds. When it breaks through the crust, it erupts in small but violent volcanoes.
I like to think of these as volcanoes of opportunity. These roads, they picked up the diamonds from their safe deposit boxes deep in the earth, about 200 kilometers down, and then were explosively erupted.
At the surface, magma builds up a mound of volcanic material that eventually cools and hardens. Hidden within the rock are diamonds, incredibly rare, perfectly formed crystals surrounded by kimberlite. Rarer still are blue boron-rich diamonds, like the Hope. Less than 1 in 100,000 form this way. "4 billion years from a dying star to the Earth's surface. Yet in a matter of days, scientists aim to turn raw carbon into super diamonds."
In order to produce anything of that nature, it would require extraordinarily high temperatures and pressures. It turns out that it's not very easy to transform graphite into diamond.
The attempt began in the 1950s, when General Electric launched Project Superpressure. Their goal, to create the first synthetic diamond. They developed machines to crush graphite at nearly 800,000 pounds per square inch and heat it above 2,500 degrees Fahrenheit, replicating the very forces in the Earth's mantle. It takes 5 years and millions of dollars, but finally, in February 1955, GE announces they've done it. the world's first synthetic industrial diamond. Over 50 years later, just outside Johannesburg, South Africa, a lab called Element 6 continues the quest for synthetic diamonds. Following GE's lead, they synthesize diamonds on a mass scale, not for jewelry, but for heavy industry. Scientist Richard Botkin is a pioneer of industrial diamond research.
We have banks and banks of presses that are capable of producing diamonds in no fewer than 45 minutes. To see such technology room after room is absolutely amazing.
The diamonds they produce start as a highly pure form of graphite powder. It's baked inside a pressure chamber between 2,500 and 3,600 degrees Fahrenheit.
Effectively, you're stacking 20 sedan motor cars on it and heating it between 1,400 and 2,000 degrees Celsius.
The result is a diamond 50% harder than those found in nature. And Element 6 can produce handfuls. These diamonds have revolutionized the drilling and mining industries. The friction from drilling into hard rocks, like granite, generates high temperatures that can damage ordinary drills. But diamond tip drills transmit heat away from the drill tip.
Oil and gas drilling benefits immensely from diamonds simply because we can drill faster and deeper with diamonds.
One shortcoming: industrial diamonds are small. The next challenge is to create diamonds large enough to be printed with circuit boards or shaped into other high-tech devices. It's a challenge that the Sarasota, Florida company Genesis is tackling. Using a special machine, they actually grow large diamonds. They start with a seed, a microscopic diamond, either natural or artificial, and surround it with graphite. It's a delicate process that shows how hard it is to create large diamonds. In charge of the process is Chief Operating Officer Clark McEwen.
We take graphite and we put it along with an actual diamond seed into an environment that emulates what happens within the Earth.
These two forms of carbon, the diamond seed and the graphite, are placed inside the chamber, where they're heated and crushed by a powerful hydraulic press.
As you apply that temperature and pressure, what happens is that graphite turns into individual carbon atoms. And those atoms permeate down and it finds that diamond seed and it attaches to it. It acts as a template.
As the graphite melts, it releases carbon atoms, which crystallize on top of the diamond seed. Molecule by molecule, the diamond grows. What nature does in 4 billion years, they do in 4 days. The result? A large artificial gem, up to 3 times larger than the seed. With this breakthrough, scientists can now consistently make large diamonds. But the real breakthrough that scientists need is yet to come. Genesis can't grow diamonds in the shapes needed for high-tech use.
We haven't gotten there yet, but we're constantly working on improving the process and making larger and better quality diamonds.
Scientists are trying to create a large diamond with all the properties of a real diamond, but in shapes and sizes not found in nature. From circuit boards to scalpel blades, the uses could be endless. As scientists struggle to perfect the diamond, a clue hurtles toward Earth from an unlikely place. After years of research, scientists discovered how to make gem-sized diamonds. One hurdle remains to making a true super diamond, making them in any shape and size. Science needs a breakthrough, and it comes from space. These strange objects look like burnt stones. They've been found in South America and Central Africa. Tests reveal a surprise. The stones are actually diamonds, black diamonds.
These are two of the famous black diamonds called carbonado because of their similarity to charcoal.
Carbonado has been known for centuries, but how it forms remains a mystery. Only recently has its potential value to science emerged. George Harlow of the American Museum of Natural History is investigating what makes carbonado so special.
Carbonado is a conundrum because it doesn't have the characteristics that we associate with diamonds that formed in the mantle on Earth.
Diamonds originating in Earth's mantle form under immense pressure and high temperature, so they're compact and dense. Not black diamonds. Using a microscope, scientists find they're riddled with holes.
It's got a lot of void space in it. Now, deep within the Earth, the void would have to be filled with something. Well, the something ain't there.
Normal diamonds contain very little void space. As they form deep in the Earth, they're crushed into a single crystal. Carbonado seems to form differently. Unlike normal diamonds, it's composed not of one crystal, but millions, all linked together. Scientists conclude carbonado formed not under high pressure, like normal diamonds, but low pressure. But just where does carbonado come from? Once again, research leads to the last gasp of a dying red giant.
The current theory for the origin and genesis of carbonado is that the small diamonds formed in supernova explosions.
Haggerty believes the vacuum of space explains carbonado's unique structure.
The diamonds were hot, one diamond bashing into the other, and they finally became glued to form a larger diamond.
During its explosive formation, specks of mineral dust are also trapped, making the large diamond appear black. The diamonds are then transported to Earth by a meteorite.
When the meteorite hit, it showered diamonds, so this must have been a truly amazing sight, with carbonado diamonds being liberated from the meteorite on impact.
It's not just the large size of space diamonds that fascinates scientists. Carbonado has another advantage over regular diamonds. Its multi-crystal structure makes it not only larger, but tougher. It's almost impossible to cut. Not so a natural diamond. Although it's one of the hardest materials known, it has its weaknesses.
You know, diamond's incredibly hard, but it can be broken along certain planes. They're called cleavage planes. And it just happens that there's certain directions in diamond where there are fewer strong bonds, and that's the direction the diamond opens.
A natural single crystal diamond will split cleanly where its chemical bonds are weakest. By following this cleavage plane, a gem cutter can split the stone perfectly. For scientists, this weakness in single crystal diamonds is a fatal flaw. Diamonds that might fracture aren't durable enough for high-tech use. The key to making a tough super diamond lies in replicating Carbonado's multi-crystal structure. Their theory of how Carbonado forms in the vacuum of space yields another breakthrough. A whole new way to make diamonds.
The space diamonds have now taught us that in fact we don't need pressure at all. This can be done in a vacuum.
Carbonado sets the stage for a new kind of super diamond. One tougher and larger than ever. That can be made into multi-crystal shapes not found in nature. The key is using low pressure to simulate the vacuum of space.
How do you make a diamond in a vacuum when diamond's only stable at high pressure? And the way you do it is by fooling the carbons into being so energetic, so excited, that when you cool them down, they find a more stable configuration. And the first one they find is diamond. And they don't go any farther.
This process is called chemical vapor deposition, CVD for short. It begins with a tiny diamond seed sealed inside a vacuum chamber slightly below atmospheric pressure. The chamber is heated to 3,600 degrees Fahrenheit. Then methane, a carbon-bearing gas, is pumped in. Then hydrogen. The gases are bombarded with microwaves, which agitates them, forcing the hydrogen and methane molecules to collide. This process releases a cloud of carbon atoms that settle on the seed, and gradually, the diamond grows. This was the seed they started with. 24 hours later, it doubles in size. At the U.S. Naval Research Laboratory in Washington, D.C., James Butler is taking this CVD process to the next level. They're growing not single stones, but wafer-thin diamond sheets.
One of the materials we grow starts with a non-diamond material, for example, a silicon wafer, onto which we put a very thin layer of these little diamond seeds. Think about shaking salt onto the kitchen table and having a whole bunch of salt crystals there. And then we put them in the CVD environment, and they will grow. And as they grow together, they bump into each other and they become this mass. So it's all diamond, but with many different grains of different orientations.
Each diamond crystal bonds to another to form a mesh of crystals across the wafer, less than a 50th of an inch thick. They can be made up to 8 inches wide. The shape of the template determines the shape of the diamond sheet. Perfect for making a wafer to replicate silicon. They're much tougher than natural diamonds. They conduct electricity and resist extreme heat. These are true super diamonds. Super diamonds have been filmed with image intensifiers that show how much more efficient diamonds are at conducting heat than the copper traditionally used in electronic components. The left plate is made of synthetic diamond. On the right, copper. The two plates are placed in ice and attached to a thermal image intensifier which records heat as it travels through an object. As the diamond plate on the left shows, it conducts heat faster than copper, up to 5 times faster. It's this unparalleled quality that puts the super in super diamond. Scientists are excited. For the first time, they have a material that could challenge the domination of silicon. Microchips made from diamond wafers can run electronic devices at higher speeds and with more power without overheating. Faster, smaller, and more efficient. Razor-thin computers, long-lasting cell phones, and picture-perfect TV screens.
I think the future of diamond is very exciting. Particularly, I think CVD diamond opens up what many of us have been calling the new diamond age.
Electronics are only the beginning. Today, scientists can make diamonds in shapes and sizes for uses that could revolutionize tomorrow. Researchers at the Carnegie Institution in Washington are trying to solve some of science's biggest mysteries. From how compressed gas can conduct electricity to how microscopic life can survive in extreme conditions. These investigations need extremely high pressures, which they create using a powerful vise called a diamond anvil cell. It squeezes an object between 2 diamond tips, creating a tiny environment of high pressure between them. It can recreate forces as extreme as pressure in the center of the Earth. For the Carnegie team's experiments, this wasn't extreme enough. But when they pushed the pressure higher, they hit a snag. The diamond shattered. Russ Hemley, director of the Geophysical Lab, decided to upgrade the anvil by making an ultra-hard super diamond.
Well, our group has been very interested in using diamond for high-pressure experiments for many, many years. And we basically needed to take this to the next level. We needed better diamond, stronger diamond, larger diamond than could be provided by Mother Earth or from conventional processes.
To create his super diamond, Hemley used a version of the CVD method to speed up the growth rate. The team then exposed the crystals to a high-pressure, high-temperature treatment to further harden them. The result? Another leap forward for super diamonds. The diamond not only grew many times faster, it also grew bigger. 15 carats. In just 6 days, they'd created a stone 1/3 the size and 50% stronger than the Hope Diamond. A gem that took nature billions of years to forge. The new super diamond was so tough, it broke Hemley's hardness gauge. When used in the diamond anvil, this new super diamond proved the breakthrough he needed.
This can produce pressures that are millions of times the pressures found at the surface of our planet.
Now, he can simulate forces so extreme they've never been studied before. Like those deep in the Earth's mantle, where pressures reach up to 1,300 kilobars. That's nearly 20 million pounds per square inch. This improved instrument lets Hemley study some of our biggest questions, like is there life in outer space? Hemley's team takes 2 common strains of bacteria, including E. coli. They place them in a liquid and crank up the super diamond anvil. the liquid turns into a dense form of ice. Under the intense pressure, most of the bacteria are destroyed. But incredibly, 1% survive. If bacteria can survive these harsh conditions, maybe life exists in outer space, perhaps on other planets. Thanks to superdiamonds created under low pressure, diamonds will reshape the future. Superdiamonds will change communications everywhere, especially on the battlefield. In constant use and battered by the elements, equipment like radios often break down in the harsh conditions of combat. But imagine if they were made of superdiamonds. Already, they can be shaped into tiny sound transmitters called nanoresonators, making vital radios and computers more robust and efficient. They can vibrate up to 100 billion times per second to create the highest quality sound yet achieved. Yet, they're tough as nails. All this from a diamond 1,000 times smaller than the width of a human hair. It's not just soldiers who will benefit. Diamond resonators will eventually be used in everyday devices like cell phones, allowing longer talk time and crystal clear reception. The same sparkle that attracts us to diamond jewelry reveals another of its secrets, its clarity.
It's transparent to light. It slows down light that passes through it.
As light enters a diamond, the dense carbon structure slows it down to less than half its normal speed. As it reflects inside the stone, the light appears to hang around longer.
You can actually force light to completely internally reflect and come out at some other angle. That's why diamonds look radiant, because light comes in from one direction, comes out another. It makes you think it's generating its own light, but it's not. All it did was redistribute the light coming in from other angles. It's remarkable.
Now you know why diamonds sparkle. The unique optical clarity of diamond, the perfect material for high-tech optical uses. Diamond is transparent across a huge spectrum of light, from ultraviolet to infrared. It's the only substance through which light passes virtually unaltered. From super diamonds, NASA can make super hard, super clear windows. The possibilities for super diamonds are endless. Soon, you may find a diamond everywhere, from your desk to your galaxy.
The future of diamond, we're just seeing the very beginning of it, and I mean the stars are the limit when it comes to what we're going to be able to do with diamond in the future.
Nature took billions of years to perfect the diamond. Now, we make super diamonds in days. Tougher, bigger, and better.
The new synthetic diamonds, that's a technology that's going to take us places we've never been before. It's going to take science in new directions. It's going to allow us to do things we could never do before. So the natural diamond, we treasure that as an object. The synthetic diamond, that will give us knowledge.
Like steel, transistors, and silicon, synthetic diamonds could revolutionize life. Welcome to the age of super diamonds.